Hello, and welcome to the Sleepy Science channel. I'm glad you found your way here tonight. Perhaps your day was long and full, or perhaps you're simply the kind of person who finds it easier to let go of the world when your mind has something quiet and vast to rest against. Either way, this is your space now. There is nothing left to do, nowhere else to be. Let your body settle. Let your breathing slow. Let the weight of the day dissolve gently like mist. Tonight we are going somewhere extraordinary. Not far from your bed, but far from everything familiar. We are drifting through the Milky Way, our home galaxy. A vast and slowly turning spiral of stars, dust, gas, and mystery, more than 13 billion years in the making. From its outermost edges to the strange and powerful heart at its center, the Milky Way is filled with secrets. Ancient stars, invisible forces, worlds without suns, and questions that the greatest minds on Earth are still working to answer. We will move through it all gently tonight. No rush, no urgency. Just one quiet wonder at a time, carrying you deeper into rest with every word. And if this kind of calm, curious exploration helps you unwind at the end of your day, please consider liking and subscribing to the channel. It helps others find their way here too, one sleepy mind at a time. Now, let's begin. The Milky Way may feel like a stable and permanent home. But look closely enough, across deep time, across billions of years, and you find that it is not a pristine creation. It is a structure assembled from the ruins of others. Over the course of its long life, our galaxy has drawn smaller galaxies toward it, pulled them apart with gravity, and absorbed their stars into its own body. The remnants of these consumed companions can still be found, scattered through the halo, woven into stellar streams, drifting in long arcs around the disk. One small galaxy, known as the Sagittarius Dwarf, is being dismantled even now, its stars slowly peeling away and threading into the Milky Way's outer regions. And the process is not finished. Far across the night sky, faint and barely visible to the naked eye, the Andromeda Galaxy is drifting steadily closer. Two great spirals, separated by more than 2.5 million light-years, drawn together by the oldest force in the universe. In roughly 4.5 billion years, they will meet. It will not be a violent crash in the way we might imagine. Stars are spaced too far apart to collide directly. But the shapes of both galaxies will be transformed forever. Long tidal arms will stretch outward. The spirals will warp and fold. And from their meeting, something new and vast will emerge. Even galaxies, it turns out, are not permanent. They grow, they merge, and they begin again. Not every star in the Milky Way was born here. Some of the most ancient stars in the galaxy, faint, slow-moving wanderers in the outer halo, appear to have formed even before the Milky Way had fully taken shape. Astronomers believe these stars originated in smaller primordial galaxies that existed in the early universe. When those ancient systems drifted too close to what would become the Milky Way, they were absorbed. Their stars became ours, but they carry the memory of their origins in their chemistry. These stars contain almost none of the heavy elements found in younger stars. No iron to speak of, almost no calcium, very little beyond the hydrogen and helium that the Big Bang itself produced. They were forged in a universe that had not yet had time to enrich itself. They move differently too. While most stars in the disk orbit in a relatively flat, orderly plane, these ancient wanderers follow long, tilted paths, looping high above and below the galaxy's main structure, as if they never quite settled into the rhythm of the spiral they now call home. In their dim and patient light, we glimpse a universe that was younger, rawer, and still in the first stages of becoming what it is. Right now, without any sensation of motion, you are traveling at extraordinary speed. The solar system orbits the center of the Milky Way at more than 828,000 kilometers per hour. That is roughly 230 kilometers every single second. And yet, because the galaxy is so incomprehensibly vast, even that astonishing speed barely registers against the scale of the journey. One complete orbit around the galactic center takes approximately 225 million years. Astronomers call this span a galactic year. In the entire 4-6 billion year lifetime of the solar system, We have completed this journey only about 20 times. 20 slow loops around a galaxy that contains more than 100 billion stars. Consider what those laps have witnessed. When the first dinosaurs appeared on Earth, our solar system occupied a completely different region of the galaxy. The stars visible in that ancient sky were not the ones we see tonight. And the stars we see now will not always be our neighbors. Everything is in slow, continuous motion, drifting and shifting across timescales too large for the human mind to fully hold. Even as you lie still, the Earth turns beneath you. The Moon traces its arc, and the entire solar system sweeps silently forward through a galaxy that has never, not once in its long existence, stopped moving. Ancient as it is, the Milky Way is not complete. It has not finished becoming what it will be. Even now, our galaxy continues to gather material from its surroundings. Cold gas seeps in from the vast intergalactic medium, the near-empty space between galaxies, providing fresh raw material for future generations of stars. Dwarf galaxies that wander too close are caught by the Milky Way's gravity, drawn inward, and slowly dismantled, their stars scattered into the halo or the disk. Dark matter continues to accumulate in the galaxy's enormous outer halo, deepening its gravitational reach. This growth does not happen like the growth of a living thing. There is no intention, no direction, no urgency. It happens the way gravity always works, patiently, inevitably, across spans of time that dwarf all of human history. Some of this accretion is quiet. Gas clouds drifting in, cooling, settling. Other episodes are more dramatic. A satellite galaxy torn apart, its stars flung in long streams across the sky. But in every case, the result is the same. The Milky Way today is larger and more complex than the one the first dinosaurs inhabited. And the one that exists a billion years from now may be larger still, stitched together, as always, from the remains of smaller worlds. Here is something surprising. We do not know with certainty how many spiral arms our own galaxy has. It seems like it should be a simple question, a matter of looking up and counting. But we live deep inside the Milky Way's disk, embedded in the very structure we are trying to map. Dense clouds of interstellar dust block our view of distant regions. Stars blur together at great distances. The geometry of our own position makes it extraordinarily difficult to see the whole. For decades, the leading model held that the Milky Way has 4 major spiral arms. More recent surveys using infrared and radio telescopes have complicated that picture. Some observations suggest that 2 of the arms may be more prominent than the others, with the remaining structures being shorter, fragmentary spurs, rather than true continuous arms. Others indicate that the arms twist and branch in ways that resist simple classification. The Milky Way may not be the neat, symmetrical pinwheel that appears in illustrations. It may be something more irregular, a living, layered swirl of stars and gas, shaped by forces we are still working to fully understand, and still revealing its true form to us, slowly, one observation at a time. Most stars spend their entire lives in a kind of quiet gravitational loyalty, orbiting the galactic center on steady, predictable paths. But there are exceptions. This emission is faint, but hydrogen is so abundant that it produces a measurable signal from gas clouds distributed throughout the disk and well beyond. By measuring the 21-centimeter emission across the sky, and using the Doppler shift of the signal to determine how fast each emitting cloud is moving toward or away from us, astronomers can map the 3-dimensional distribution of hydrogen gas throughout the galaxy. This technique has revealed the spiral arm structure of the Milky Way more clearly than any optical survey, and has traced the warp of the outer disk, the extent of the galactic bar, and the presence of gas clouds far beyond the visible edge of the stellar disk. The galaxy has a voice we cannot hear. Radio astronomy taught us to listen, and in doing so, transformed our understanding of the structure we inhabit. The Sun, as it exists today, is a solitary star. No companion star orbits it. No stellar sibling shares its immediate neighborhood. In the vast and sparsely populated region of the Orion Spur that the solar system currently occupies, the nearest star beyond our own, Proxima Centauri, lies more than 4 light-years away. To all appearances, the Sun travels through the galaxy alone. There are stars that are flung. But this was not always the case. And the solitude of our sun's present situation is almost certainly not the condition of its birth. Stars form not in isolation, but in groups, clusters of tens, hundreds, or thousands of siblings, all condensing from the same collapsing molecular cloud within a relatively short span of time. The shared chemistry of their parent cloud means they are born with similar compositions. The shared timing of their formation means they are born with similar ages. And for their first millions of years, they share the same region of space, moving together as a gravitationally bound family. The Sun, according to our best understanding of stellar formation, was born in such a cluster, a compact family of perhaps hundreds to thousands of stars, all arising from the same cloud of gas and dust somewhere in the Milky Way approximately 6 billion years ago. For a time, those sibling stars were its nearest neighbors. The young solar system formed and grew in their company, under the combined radiation and gravitational influence of hundreds of nearby suns. Then, as always happens, the cluster began to dissolve. Deep at the heart of the Milky Way, where the density of matter is extreme and the gravity of a supermassive black hole dominates everything nearby, rare and violent events can occur. Tidal forces from the galaxy, gravitational interactions between cluster members, and the general dynamics of the disk slowly pulled the siblings apart, sending each on its own independent orbit through the galaxy. The family scattered. The Sun continued alone. Those siblings are still out there, somewhere in the Milky Way, following their own orbits, aging at the same rate as our own star, carrying the same chemical fingerprint from the same ancient cloud. We simply have not yet found them. The dissolution of the Sun's birth cluster happened so long ago that no obvious trace of the original grouping remains. The stars that formed alongside our Sun have had 6 billion years to disperse, drifting apart under the influence of galactic tides, nudged onto diverging orbits by passing stars and molecular clouds, scattered across a volume of space so large that finding any individual member among the galaxy's hundreds of billions of stars would seem, at first consideration, hopeless. But astronomers are trying, and they are finding reasons for cautious optimism. The key to locating the Sun's siblings lies in the fact that stars formed from the same molecular cloud share a distinctive chemical signature, a pattern of elemental abundances that reflects the specific composition of the gas from which they condensed. When a binary star system, two stars orbiting each other, drifts too close to the black hole, the encounter can be catastrophic. This signature is not universal. Different clouds in different regions of the galaxy at different times have different compositions, and the resulting stars carry those differences in their spectra, preserved across billions of years. By precisely measuring the chemical compositions of large numbers of stars and comparing them to the Sun's own composition, astronomers can identify candidates, stars whose elemental fingerprints suggest a shared origin. The Gaia spacecraft, combined with large spectroscopic surveys, has made this kind of search more feasible than ever before, providing precise measurements of stellar positions, motions, and, in conjunction with other instruments, compositions, for enormous numbers of stars simultaneously. A handful of promising candidates have been identified. Stars of the right age, the right chemistry, and orbital histories that are at least broadly consistent with having originated in the same region of the galaxy as the Sun. Whether any of them are genuine siblings remains to be confirmed. But the search itself is an extraordinary undertaking, an attempt to reconstruct, across billions of years and thousands of light years, the family from which our Sun came. The warp of the Milky Way's outer disk, the gentle upward curve on one side and downward bend on the other, is a feature we have already noted in the context of the galaxy's overall shape. But the warp is not simply a fixed deformation, like a bent coin that has been permanently misshapen. It is a dynamic feature. The black hole captures one star, pulling it inward to an irreversible fate. It moves. Evidence from recent stellar surveys, and particularly from data released by the Gaia spacecraft, suggests that the warp of the Milky Way's disk is rotating, precessing, in the technical language of dynamics, around the galactic center. The high point of the warp, the region where the disk bends most prominently upward, is not fixed in space. It moves, completing a slow rotation around the galaxy on a timescale of hundreds of millions of years. This behavior is consistent with the warp being driven by an external gravitational influence, most likely the combined effect of the Magellanic Clouds, whose combined mass and proximity exert a gravitational torque on the outer disk that causes it to wobble in a manner analogous to the precession of a spinning top under the influence of gravity. As the Magellanic Clouds move in their own orbits around the Milky Way, the direction of their gravitational pull slowly changes, causing the warp to precess in response. Alternatively, or additionally, misaligned dark matter substructures moving through the halo could contribute to the wobble, their gravitational influence tilting the disk as they pass. Either way, the outer galaxy is not still. It ripples and wobbles on timescales of hundreds of millions of years, its edges rising and falling in a slow, majestic oscillation driven by the gravitational company it keeps. From far enough away, the Milky Way would not look like a still plate. The other is released with tremendous force, hurled outward at speeds exceeding 1,000,000 kilometers per hour. It would look like one that is, imperceptibly but genuinely, rocking. The word tides most naturally calls to mind the ocean, the rise and fall of water driven by the gravitational influence of the moon acting unevenly on different parts of the Earth. Near side pulled more strongly than far side. The difference in force stretching and distorting the body caught within it. The same principle operates at every scale in the universe, including at the scale of the galaxy. The Milky Way, with its immense and unevenly distributed mass, exerts gravitational forces on every object within it. And because the force of gravity decreases with distance, the pull on the near side of an extended object, a star cluster, a dwarf galaxy, a globular cluster, is always slightly stronger than the pull on the far side. This differential force is the galactic tide, and over sufficient time, it is extraordinarily effective at pulling things apart. Star clusters are among the most visible victims of this process. A young open cluster, freshly emerged from its parent molecular cloud, may be compact and relatively tightly bound. These are called hypervelocity stars. But as it orbits the galactic center over hundreds of millions of years, the tidal field of the galaxy slowly stretches it, pulling stars from the edges, smearing them along the cluster's orbital path into a structure called a tidal stream. Over billions of years, the cluster loses more and more members to this process, its population declining and its spatial coherence dissolving until it exists only as a faint, elongated overdensity in the stellar field, and then not even that. Dwarf galaxies experience the same fate on a grander scale. Those that orbit too close to the Milky Way are gradually dismembered, their stars drawn out into the long stellar streams we have already discussed, their gas stripped away, their dark matter halos slowly absorbed into the larger structure. The galactic tide does not break things suddenly. It unravels them, patiently, persistently, over timescales that exceed the age of the Earth many times over. It might seem reasonable to expect that among the most basic facts we would know about our own galaxy, the system we inhabit, the structure we have been observing and studying for centuries, would be its total mass. Mass, after all, is the most fundamental gravitational property of any object. It determines how stars orbit, how satellite galaxies behave, how the galaxy interacts with its neighbors. Surely knowing our own home galaxy's mass would be among the first things we would establish. And they travel alone. And yet the total mass of the Milky Way remains, at present, one of the less precisely known quantities in galactic astronomy. The difficulty is not in measuring the visible component. The mass of all the stars, gas and dust in the galaxy, the ordinary matter we can detect directly, is reasonably well constrained. The problem is the dark matter halo. The halo dominates the total mass budget of the galaxy by a large factor, but because it emits no light and interacts with ordinary matter only through gravity, measuring it requires indirect methods. The most reliable approach uses the motions of objects at large distances from the galactic center, stars in the outer halo, globular clusters, and satellite dwarf galaxies, as traces of the total gravitational potential. The faster these objects move and the farther out they are found, the more mass must be present to keep them bound. But measuring the true three-dimensional velocities of objects at such distances is observationally challenging, and the results carry significant uncertainties. Current estimates for the total mass of the Milky Way, dark matter included, range from roughly 500 billion to over 2 trillion times the mass of the Sun. The factor of 4 uncertainty in that range represents a genuine and ongoing challenge, one that future observations, particularly from the Gaia mission and its successors, are expected to progressively reduce. We know our home galaxy well in many respects. Far from the galactic plane, far from any stellar neighborhood, they race outward through the halo and beyond, glowing quietly like embers thrown from a fire on trajectories that will carry them out of the Milky Way entirely and into the vast dark between galaxies. Its mass in its entirety remains elusive. For much of the history of modern astronomy, Andromeda has been regarded as the larger and more massive of the two great spirals that dominate the local group. It appears larger on the sky. Its angular extent, even to the naked eye, is several times the width of the full moon. Its total stellar population is estimated to be somewhat greater than the Milky Way's. It has more satellite galaxies. By most visible measures, Andromeda seems the grander of the two. But visible measures may be misleading, and recent evidence has begun to complicate the traditional picture. The total mass of a galaxy is determined not by its stars alone, but by the full extent and density of its dark matter halo, a component that cannot be measured by looking at the galaxy's light. When astronomers attempt to measure the dark matter halos of both the Milky Way and Andromeda, through the motions of their respective satellite galaxies and outer halo stars, a different picture begins to emerge. Several recent studies, using data from the Gaia spacecraft and other sources, suggest that the Milky Way's dark matter halo may be broader and more massive than previously believed, potentially comparable to or even exceeding that of Andromeda. They will never return. If these measurements are correct, the Milky Way may actually be the more massive of the two galaxies, despite its less imposing visible appearance. This matters for more than reasons of galactic pride. The relative masses of the two galaxies will directly shape the dynamics of their eventual merger. Which galaxy's center becomes the nucleus of the combined system, how the tidal tails form and extend, what the resulting merged galaxy ultimately looks like. If the Milky Way is the heavier partner, the encounter may unfold differently than simulations based on Andromeda's dominance have suggested. Our galaxy, it seems, may carry more weight than it shows. Visible from the southern hemisphere as two bright, irregular patches of light, one larger and one smaller, hanging in the sky like detached fragments of the Milky Way, the large and small Magellanic Clouds have long been regarded as the galaxy's closest and most familiar companions. Their proximity, their brightness, and their visibility to the naked eye have made them objects of fascination and study for millennia, and they have featured prominently in the astronomical traditions of peoples throughout the southern world. For most of the history of modern astronomy, they were assumed to be long-standing satellite galaxies of the Milky Way, companions that had been orbiting our galaxy for billions of years on repeated close passes, their shapes and stellar populations gradually modified by the tidal forces of each encounter. But this comfortable picture has been significantly revised by more recent measurements of the cloud's velocities through space. When astronomers used data from the Hubble Space Telescope and later from Gaia to measure the true three-dimensional motion of the Magellanic Clouds with precision, they found something unexpected. They carry with them, silently, a record of the violence that set them free. The clouds are moving substantially faster than they should be if they were in a long-established orbit around the Milky Way. Their velocities are, in fact, close to or possibly exceeding the escape velocity of the galaxy. This suggests that the Magellanic Clouds are not long-term residents. They may instead be recent arrivals, dwarf galaxies that have spent most of their lives in a different part of the universe, far from the Milky Way, and are now making their first close approach to our galaxy. What we are witnessing in this scenario is not a familiar relationship between established companions, but a first encounter, one that is already reshaping the outer disk of the Milky Way and will continue to influence the galaxy's structure for billions of years to come. Wherever the Magellanic Clouds have come from, and however long they have been in the Milky Way's vicinity, they have not traveled undisturbed. The gravitational forces they have encountered, from each other and from the Milky Way, have left their mark in a spectacular and enormous structure that stretches across a vast arc of the southern sky. This is the Magellanic Stream, a ribbon of neutral hydrogen gas stripped from the Magellanic Clouds by tidal forces and by the ram pressure of the hot gas that pervades the Milky Way's halo, stretched across more than 150 degrees of sky and spanning hundreds of thousands of light-years in physical extent. It is one of the largest coherent structures associated with our galaxy, and yet it is entirely invisible to the naked eye, detectable only in radio wavelengths, where the 21-centimeter emission of neutral hydrogen reveals its presence in exquisite detail. The stream is not a simple ribbon. In the Milky Way, the overwhelming majority of stars orbit the galactic center in the same broad direction, a shared rotation inherited from the original collapse of the galaxy's gas and dust long ago. It has a complex, multi-stranded structure, with different filaments having been stripped at different times and from different parts of the clouds. It also has a leading component, gas that lies ahead of the clouds in their orbital motion, and a trailing component that extends behind them, marking the path they have recently traveled. The eventual fate of the stream is a matter of ongoing study. As it moves through the hot halo gas of the Milky Way, it is subject to heating and disruption, the individual hydrogen clouds within it slowly evaporating and mixing with the hotter medium around them. Some of the gas may eventually cool and condense, raining down onto the Milky Way's disk and contributing to future star formation. Other portions may disperse entirely, their contents dissolving into the halo and becoming indistinguishable from the surrounding medium. Either way, the stream is a testament to the dynamic and ongoing relationship between the Milky Way and its most prominent companions, a visible record of the gravitational forces that bind and shape the local group, written in cold hydrogen across a vast arc of sky. The plane of the Milky Way's disk is the natural home of most of the galaxy's gas, the dense, organized star-forming medium that populates the spiral arms and fuels the ongoing cycle of stellar birth and death. Gas in the disk follows orbits that are broadly aligned with the rotation of the galaxy, confined to within a relatively thin layer above and below the equatorial plane. But some gas does not follow these rules. But not all stars follow this pattern. Some clouds orbit the Milky Way on paths that are highly inclined to the disk, tilted at steep angles, in some cases nearly perpendicular to the galactic plane. These are called high-velocity clouds, or in extreme cases of inclination, polar ring structures, gas that moves above and below the galaxy on orbits more reminiscent of the tilted paths of halo stars than of the orderly planar motion of disk gas. The origins of these inclined gas clouds are almost certainly external. Gas that formed within the disk and has always been part of the galaxy's internal cycling would naturally share the disk's orbital orientation. It would have no mechanism for developing the steep inclinations observed. Gas arriving from outside, by contrast, can arrive at any angle. Dwarf galaxies absorbed at steep orbital inclinations contribute their gas at those inclinations. Filaments from the cosmic web, accreting onto the galaxy from directions not aligned with the disk, can deposit gas on highly tilted paths. The Magellanic Stream itself contributes gas at inclinations quite different from the disk. These polar and inclined gas clouds are, in a sense, the galaxy's way of remembering the directions from which its material arrived, orbital fossils of accretion events that have long since concluded, preserved in the slow, tilted drift of gas clouds still following the trajectories they were set upon long ago. Distributed across the Milky Way, in various stages of expansion and dissolution, are structures of striking geometry, vast, roughly spherical shells of gas, each one marking the site of an event that may have occurred millions of years ago and yet left a scar large enough to span hundreds of light-years of interstellar space. Some move against the current entirely. These supershells are the remnants of starbursts, episodes of unusually intense and concentrated star formation in which large numbers of massive stars formed in the same region of space and within a relatively short period of time. Those massive stars lived their brief, brilliant lives and then died in rapid succession, producing supernovae one after another over a span of millions of years. The combined energy of these explosions, far greater than any single supernova event, drove an expanding wave of gas outward in all directions. As the shock wave expanded, it swept up the surrounding interstellar medium, compressing it into a dense shell and leaving a hot, rarefied cavity within. The expanding shell continued to grow, slowing as it swept up more and more material, cooling as it expanded, but maintaining its coherent, roughly spherical shape for timescales of tens of millions of years. What remains today is the ghost of that ancient creative violence. A shell of compressed gas, still slowly expanding, its interior now largely evacuated, and its walls marked by ongoing star formation triggered by the compression of the swept-up material. In some cases, these shells interact with one another, neighboring starbursts whose expanding remnants collide and merge, producing even more complex structures in the interstellar medium. They are the rings left in the water by stones thrown long ago, expanding, fading, but still carrying outward the memory of the moment of impact. The vastness of interstellar space makes stellar collisions seem, at first consideration, essentially impossible. Certain stars, particularly those found in the outer halo, travel in retrograde, orbiting in the opposite direction to the galaxy's main rotation. The distances between stars are so enormous, even in the densest regions of the disk, that the probability of two stars actually making physical contact during the lifetime of the galaxy seems vanishingly small. And in the general field of the Milky Way, this intuition is correct. Stars essentially never collide. But the general field of the Milky Way is not the only environment the galaxy contains. Within the cores of globular clusters, those ancient compact spheres of hundreds of thousands of stars that orbit the galaxy in the halo, the situation is dramatically different. At the center of a globular cluster, stellar densities can be thousands or even millions of times higher than in the solar neighborhood. Stars are not separated by light years. They are separated by distances measured in fractions of a light year, or in some cases by distances not much greater than the diameter of our own solar system. In these extraordinarily crowded conditions, close stellar encounters are not rare events. They are routine. They are not defective or unusual in their composition. Stars pass near one another regularly, their gravitational fields interacting in complex ways, exchanging energy and angular momentum, altering one another's orbits. And occasionally, rarely, but over billions of years, inevitably, two stars pass close enough to actually merge. When they do, the result is a new object with a combined mass greater than either of its progenitors. If the collision involves two stars that have aged significantly, stars that have used up much of their hydrogen and should, by rights, be entering the later, redder stages of stellar evolution, the merged product may instead appear young and hot and blue, as if it had just formed. These anomalous objects are called blue straggler stars, and they are found in the cores of globular clusters throughout the Milky Way. In the densest stellar cities in the galaxy, time moves differently. The rules that apply in the quiet suburbs of the disk do not fully apply in these ancient, crowded cores. And the stars within them tell stories that the general stellar population never could. A significant fraction of stars, estimates vary, but likely more than half of all stars in the Milky Way, do not travel through the galaxy alone. They exist in pairs, two stars bound together by their mutual gravity, orbiting a common center of mass in an embrace that can persist for billions of years. These binary systems are extraordinarily stable under ordinary conditions. They simply do not belong to the same rotational family as the stars around them. The same gravitational bond that holds a planet in orbit around its star is capable of keeping a stellar pair together across timescales comparable to the age of the universe. But there are conditions under which even this durable bond can be broken. Conditions under which the gravitational forces acting on the binary system from outside become strong enough and sufficiently asymmetric between the two stars to overwhelm the internal gravity that holds them together. The most extreme such environment is the vicinity of the supermassive black hole at the galactic center. As we have noted, when a binary system passes sufficiently close to Sagittarius A star, the tidal forces exerted by the black hole can separate the two stars, capturing one into a tightly bound orbit around the black hole itself, while ejecting the other outward with tremendous velocity. This is the mechanism believed responsible for at least some of the hypervelocity stars that are observed escaping the galaxy entirely. But the galactic center is not the only place where binary systems face disruption. The dense cores of globular clusters, those crowded stellar environments we have just discussed, also present a hazard. Close encounters with other stars within the cluster can alter the orbital dynamics of a binary, injecting or extracting energy in ways that tighten, widen, or ultimately dissolve the pair's gravitational relationship. In both cases, what had been a stable, long-lived partnership is ended not by any internal failing, but by the overwhelming external gravity of a larger system. The most likely explanation is origin. The galaxy, enormous and indifferent, separates companions that had traveled together for billions of years. Not violently, in human terms, but with a finality that admits no return. Most stars, for all their motion through the galaxy, remain gravitationally bound to it. They follow orbits, elliptical, circular, inclined, retrograde, or some complex combination of these, but those orbits are closed. They return. The galaxy's gravity is sufficient to hold them indefinitely, and they cycle through their paths, generation after generation, without ever approaching the threshold beyond which escape becomes possible. But some stars reach that threshold, and for them, there is no return. To escape the Milky Way's gravitational grip, a star must exceed the galaxy's escape velocity, a value that depends on position within the galaxy, but in the outer disk and halo amounts to something in the range of 500 to 600 kilometers per second. This is an extraordinary speed, far greater than the orbital velocities of typical disk stars, and achieving it requires a correspondingly extraordinary mechanism. Several such mechanisms have been identified. These retrograde stars were almost certainly born elsewhere, in dwarf galaxies or smaller structures that were later absorbed by the Milky Way. The slingshot effect of the galactic center's supermassive black hole, as discussed, is capable of producing stars with velocities well in excess of this threshold. Three-body gravitational interactions, complex encounters between three stars in which one is ejected at high speed while the other two form a tightly bound pair, can also produce high-velocity runaways. And the asymmetric explosion of a supernova in a binary system, where one star explodes and the other, suddenly unbound from its companion's gravity, flies free, is another mechanism capable of generating stellar velocities approaching or exceeding escape speed. Once free, these hypervelocity stars travel outward through the halo and eventually beyond the galaxy's edge into the intergalactic medium. They carry with them the chemical composition of the environment in which they formed, the orbital memory of the event that set them free, and, in a sense, a small piece of the Milky Way, now traveling alone through the void between galaxies. They will not return, but they will continue to move, for billions of years, through the dark between the galaxies, tiny lights in an enormous emptiness, carrying the Milky Way's signature into regions it will never otherwise reach. The Milky Way's stellar population is not composed entirely of stars born within it. Alongside the native-born stars that formed from gas clouds within the disk or halo over the galaxy's long history, there exists a population of immigrants, stars that originated in entirely different galaxies and arrived in the Milky Way through the processes of galactic merging and accretion that have shaped our galaxy across billions of years. When a dwarf galaxy is absorbed by the Milky Way, its stars do not disappear. When those systems were consumed, their stars retained the memory of their original motion, continuing to orbit in the direction they always had, regardless of the current around them. They are redistributed, scattered through the halo and sometimes the disk, but they persist, continuing to burn and orbit, now embedded in a galaxy far larger than the one in which they formed. Over time, the dynamical signature of their foreign origin fades somewhat as the galaxy's tidal forces gradually mix them into the general stellar population. But it never fades entirely. These immigrant stars can often be identified by characteristics that mark them as out of place. Their orbital properties may be unusual, following paths more inclined, more eccentric, or oriented differently from stars native to the same region. Their chemical compositions may differ, reflecting the specific enrichment history of the smaller galaxy in which they formed, which developed differently from the Milky Way's own interstellar medium. And in some cases, they travel in coherent groups, stellar streams and shells that preserve the spatial and kinematic coherence of the disrupted system from which they came. The Milky Way's halo in particular is rich with these arrivals. Detailed analyses of halo star populations have revealed multiple distinct components that appear to have originated in different accreted systems. Different dwarf galaxies, each with its own star formation history, absorbed at different times and from different directions. The Milky Way is not a single lineage. Their reversed paths are a kind of quiet signature, a gravitational accent that marks them as travelers from somewhere else. It is a mosaic, built not only from the stars it formed itself, but from the populations of many smaller galaxies that it has, across billions of years, made its own. The Milky Way's disk is not a closed system in which gas stays put indefinitely, cycling only within the plane. There is a vertical dimension to the galaxy's gas circulation, a slow, continuous exchange of material between the disk and the halo above and below it, driven by the energy released by the galaxy's most powerful stellar events. When clusters of massive stars reach the ends of their lives and explode as supernovae, and when the winds of massive stars during their lifetimes drive powerful outflows, they heat the surrounding interstellar gas to temperatures of millions of degrees. At these temperatures, the gas expands rapidly and, in the most energetically extreme cases, punches through the disk entirely, venting into the lower halo in the galactic chimneys we discussed earlier. Once in the halo, this hot gas begins to cool, slowly at first, then more rapidly as it mixes with the cooler, denser gas already present at lower altitudes in the halo. As it cools, it loses the buoyancy that kept it aloft, and gravity pulls it downward. It condenses into clouds, collections of cool, relatively dense gas hanging in the lower halo, and those clouds eventually fall back toward the disk in a gentle rain of returning material. This cycle, gas ejected upward by stellar energy, cooling in the halo and falling back down to the disk, is called the galactic fountain. And it is not merely a curiosity of galactic dynamics. The galaxy carries their foreign motion within it, the way a river carries currents from tributaries that once flowed in different directions. It is a mechanism of fundamental importance for the chemical evolution of the galaxy. As hot gas rises from the disk, it carries with it the heavy elements produced and scattered by the supernovae that drove it upward. These elements, iron, oxygen, silicon, and others, are then distributed throughout the lower halo, mixed with the infalling gas from the cosmic web, and eventually return to the disk in a form enriched beyond what the disk gas alone contained. Each cycle of the fountain increases the heavy element content of the gas available for future star formation, gradually building up the chemical complexity that makes rocky planets and the chemistry of life possible. The galaxy, in this sense, does not merely burn its fuel. It refines it, cycling its own material through the halo, enriching it with each pass, and returning it to the disk transformed. The interstellar dust that permeates the Milky Way, the microscopic grains of carbon, silicates, and ice that drift through molecular clouds, absorb starlight, and align with magnetic fields, is not merely a passive component of the galaxy's structure. It is chemically active, and the chemistry it harbors and transports across light years of interstellar space may be one of the most significant facts about the galaxy for the question of life's prevalence. On the surfaces of interstellar dust grains, and within the cold, dense interiors of molecular clouds, complex molecules form through a combination of gas phase reactions and surface chemistry catalyzed by the grain surfaces themselves. The Milky Way has not grown alone. The conditions in these environments, extreme cold, intense ultraviolet radiation at the cloud's edges, cosmic ray bombardment penetrating deep into the cloud's interior, drive a rich and varied chemistry that produces molecules of surprising complexity. Among the molecules detected in interstellar space are polycyclic aromatic hydrocarbons, large carbon ring structures that are among the most abundant organic molecules in the universe. Simple sugars have been detected, amino acid precursors, alcohols, glycolaldehyde, a simple sugar with direct relevance to the chemistry of RNA. The list grows longer with each new generation of radio and infrared telescopes capable of detecting increasingly complex molecular signatures. These molecules are not alive. They are not even close to the complex, self-replicating chemistry we associate with life. But they are the building blocks from which that chemistry might, under the right conditions, eventually assemble itself. Across billions of years, it has grown by consuming, and they are present in abundance in the very clouds from which stars and planetary systems form. When a molecular cloud collapses to form a star and a surrounding disk, the chemical inventory of the cloud goes along for the ride, incorporated into the gas and dust of the protoplanetary disk, eventually settling into the material from which comets, asteroids, and planets are made. Some of these prebiotic molecules survive the process intact. Some are delivered to young planetary surfaces by cometary impacts. Some may, on worlds with the right conditions, become part of something far more complex. The galaxy is not merely a nursery for stars. It may also be a laboratory, slowly and patiently assembling the chemical prerequisites for life and distributing them across billions of worlds. There is a continuity between the chemistry of interstellar space and the chemistry of living things. A thread, fragile and indirect, but real, connecting the molecules drifting in cold molecular clouds to the biochemistry of cells on a warm planetary surface. Understanding that thread is one of the central challenges of astrobiology, and the Milky Way itself is the laboratory in which it is being examined. The formation of a planetary system begins with the collapse of a molecular cloud, and the cloud carries with it whatever chemistry has accumulated during its long cold existence in the interstellar medium. Smaller galaxies, faint diffuse companions drifting through the local group, have been caught in the Milky Way's gravitational pull, drawn steadily inward and dismantled over time. The complex organic molecules synthesized on grain surfaces, the simple sugars and amino acid precursors that radio telescopes detect in dark clouds, the water ice that coats dust grains in the coldest regions. All of this becomes part of the material from which the protoplanetary disk is assembled. Within the disk, this chemical inheritance is processed further. Heat from the young star drives chemical reactions in the inner disk. Ultraviolet radiation photodissociates some molecules and drives the formation of others. Ice-coated dust grains aggregate into planetesimals, carrying their chemical cargo into the solid bodies of the forming planetary system. Some fraction of this material ends up in comets and asteroids, bodies that preserve the early chemical inventory of the solar system largely intact, and that can deliver it to planetary surfaces through impacts. The bombardment of the early Earth by cometary and asteroidal material is thought to have contributed significantly to the inventory of organic molecules from which life's chemistry eventually emerged. The key implication is this: the chemistry that gave rise to life on Earth did not begin on Earth. It began in a cold, dark molecular cloud long before the solar system existed, assembled over millions of years by the slow chemistry of interstellar space, and delivered to a young world by the same collisional processes that shaped its surface. If this is true of Earth, it is likely true in varying degrees of other worlds throughout the Milky Way. Their stars, once part of entirely separate systems with their own histories and motions, are now threaded through our halo, embedded in our disk, or stretched across the sky in long stellar streams. The ingredients for life are not rare. They are widespread, distributed by the same processes that distribute stars, carried within the same clouds that form planetary systems, delivered by the same impacts that shaped the early history of our own world. Stars rotate. This is a natural consequence of their formation from rotating gas clouds. The same angular momentum that causes a collapsing cloud to flatten and spin is inherited by the star that forms at its center. The Sun, for instance, rotates on its axis once every 25 to 35 days, depending on the latitude observed, a modest rotation that has slowed considerably from the much faster spin of its youth under the braking effect of its magnetic field and stellar wind. But not all stars spin so sedately. Some rotate at speeds that strain the structural limits of what stellar material can withstand. The fastest rotating stars known, many of them young, hot, and massive, complete a full rotation in a matter of hours. Their equatorial regions move at velocities of hundreds of kilometers per second, approaching a significant fraction of the orbital speed needed to remain gravitationally bound to the star itself. The centrifugal effect of this rapid rotation distorts the star's shape dramatically, flattening it at the poles and bulging it outward at the equator into a shape that can deviate substantially from a sphere. Astronomers have identified several of these ancient mergers by studying the motion and chemical composition of stars that don't quite fit the patterns of the galaxy around them. At the most extreme rotation rates, the centrifugal force at the equator approaches the star's own surface gravity. Material at the equatorial surface becomes marginally bound, and some is shed, ejected into a ring or disk of gas that surrounds the star like a miniature version of the rings of a planet. These rotationally driven disks, glowing in the ultraviolet and visible light of the hot material within them, create a class of objects known as B stars, rapidly rotating stellar objects surrounded by their own self-generated equatorial disks. The lives of these fast-spinning stars are different in other ways as well. Rapid rotation enhances the mixing of material within the stellar interior, bringing fresh hydrogen fuel into the core and extending the star's main sequence lifetime. It can drive powerful stellar winds and influence the geometry of the eventual supernova if the star is massive enough to end its life in an explosion. They are among the most dynamic stellar objects in the galaxy. Spinning sirens in the dark, briefly brilliant and structurally extreme, living fast in ways that leave their mark on everything around them. When we look up at the night sky and trace the band of the Milky Way as it arcs from horizon to horizon, we are seeing the galactic plane, the flat, star-rich disk of our galaxy, projected against the sky as it appears from our location within it. But the orientation of this band is not arbitrary, and it is not aligned with the plane of our own solar system. The ecliptic, the plane in which the Earth orbits the Sun, and along which the other planets of the solar system also move, is not parallel to the galactic plane. One of the most significant was a collision with a large galaxy now known as Gaia Enceladus, an event that occurred billions of years ago and is believed to have contributed a substantial number of stars, while also reshaping the early structure of the Milky Way's inner regions. The two planes are inclined to each other at an angle of roughly 60 degrees. This means that the plane of the solar system cuts diagonally through the galaxy's disk at a steep angle, not lying flat within it, but tilting sharply relative to the broader structure we inhabit. This misalignment has several observable consequences. Because the galactic plane is tilted relative to the ecliptic, the Milky Way does not follow a consistent path through the sky relative to the familiar markers of the ecliptic, the zodiac constellations, the path of the planets, the seasonal arc of the Sun. Instead, it crosses the ecliptic at a steep angle, appearing high overhead in some seasons and lower in others, depending on one's latitude and time of year. The tilt also means that our view of the galactic center and of different regions of the disk changes with the rotation of the Earth and the revolution of our planet around the Sun, providing astronomers in different parts of the world and at different times of year with access to different portions of the galactic structure. We are part of the galaxy, embedded within its disk. But we arrived at our current orbital inclination through the specific history of our solar system's formation, a history that left us tilted, not aligned, within the larger structure we call home. Among the populations of stars and stellar remnants distributed through the Milky Way's halo, there is a class of objects whose age carries particular significance, not merely because they are old, but because they are older than the structure most commonly associated with the galaxy itself. White dwarfs are the cooling remnants of stars like the Sun, the dense Earth-sized cores left behind when a low or intermediate mass star exhausts its nuclear fuel, expels its outer layers as a planetary nebula, and settles into a long, slow decline. Once formed, a white dwarf generates no new energy through fusion. The galaxy we live in is not an original. It simply radiates away the heat stored within it, cooling progressively over billions of years from brilliant white through yellow and orange toward the theoretical endpoint of a cold, dark body, a black dwarf, that the current age of the universe has not yet allowed any white dwarf to reach. The cooling rate of a white dwarf is well enough understood that its current temperature serves as a reliable clock. By measuring how cool a white dwarf has become, astronomers can estimate how long it has been cooling, and therefore when the star that preceded it was born. In the outer halo of the Milky Way, surveys have identified white dwarfs so cool, and therefore so old, that they must have formed before the galaxy's thin disk came into existence. Their progenitor stars were born during an earlier epoch, before the disk had settled into its current flattened configuration, in the looser and more chaotic environment that preceded the organized structure of the Milky Way we recognize today. These ancient remnants are dim and difficult to find, but each one that is identified is a direct physical link to the galaxy's earliest stellar generations, a cooling ember from a fire that burned when the Milky Way was still becoming what it is. The Milky Way does not end where its light fades. The visible disk, the luminous, star-rich spiral that dominates our image of the galaxy, is surrounded by a far more diffuse and extended population of stars that reaches outward into the halo to distances that, until recently, we could barely probe. These are the galaxy's outermost stars, and they are extraordinary objects simply by virtue of where they are found. It is not a single continuous creation. Some of the most distant confirmed members of the Milky Way have been identified at distances of 500,000 light-years or more from the galactic center, 5 times the diameter of the visible disk, drifting in a region of space so remote and so sparsely populated that the nearest neighboring star might be tens of thousands of light-years away. At such distances, the night sky as seen from any planet orbiting such a star would bear little resemblance to ours. The Milky Way itself would appear as a faint luminous smear, a distant galaxy, recognizable as a spiral only with magnification, offering no hint that the observer was actually one of its own members. These outermost stars follow orbits of extraordinary scale, paths that take billions of years to complete, carrying them through the vast and nearly empty outer halo on trajectories so wide that in the entire age of the galaxy, they may have completed only a handful of full circuits. Many are thought to have arrived at their current positions through the disruption of dwarf galaxies absorbed by the Milky Way, stripped from their original systems and deposited in the halo at large distances. Their importance extends beyond their intrinsic interest as extreme objects. By measuring the velocities of stars at large galactic distances and determining whether those velocities are sufficient to escape the galaxy's gravity or whether they remain bound, astronomers constrain the total mass of the Milky Way, particularly the mass of the dark matter halo that extends beyond any visible structure. The farthest stars are not merely the galaxy's outermost inhabitants. They are its gravitational tracers, helping us measure, in the most indirect of ways, the true extent of the invisible structure within which the entire visible galaxy is embedded. Every illustration of the Milky Way that has ever appeared in a textbook, a magazine, or a science documentary has shown essentially the same image: a graceful, symmetrical spiral, its arms curving away from the center in matched pairs, its disk flat and uniform, its overall shape as ordered and geometrically satisfying as a mathematical construction. It is a composite, assembled quietly over deep time from the remains of many smaller worlds, each one dissolved and incorporated into something larger. It is a compelling image. It is also, in important ways, a simplification. The real Milky Way is irregular. Not chaotically so. It is recognizably a barred spiral galaxy, and its large-scale structure broadly resembles the idealized images. But at the level of detail that careful observation reveals, departures from perfect symmetry are present everywhere. The spiral arms are not matched pairs of equal length and brightness. Some are more prominent, more clearly defined, and more richly populated with young stars than others. The disk is not uniformly thick. One side is measurably thicker than the other. The warp of the outer disk is itself asymmetric, rising more prominently on one side than it dips on the other. The stellar halo is not centered precisely on the galactic core, but is slightly offset, its distribution elongated in a direction that reflects the history of the mergers that assembled it. Every star in the Milky Way carries a chemical signature, a unique pattern of elements present in its atmosphere at the moment of its birth, preserved across billions of years in the light it radiates today. Even at the level of individual spiral arm segments and star-forming regions, the structure of the galaxy resists the simple, ordered symmetry of the textbook image. Arms branch and fragment. Spurs extend between major arms at irregular intervals. Star-forming regions are distributed unevenly, concentrated in some stretches of the arms and sparse in others. None of this makes the galaxy less magnificent. If anything, these irregularities make it more interesting. A structure shaped not by mathematical perfection, but by the accumulated record of billions of years of gravitational interactions, mergers, and dynamical evolution. The Milky Way's asymmetries are its history, written in the shape of stars. Among the most practically important stars in the Milky Way, and indeed in the broader universe, are a category of stars that are remarkable not for their size, their temperature, or their composition, but for their behavior. These are variable stars, stars whose brightness changes over time in a regular repeating pattern, expanding and contracting in slow luminous cycles that can be measured with precision from Earth. The most astronomically significant variable stars belong to two main classes. Stars formed in dense, metal-rich regions of the galaxy tend to contain relatively high proportions of heavy elements like iron, calcium, and silicon. Cepheid variables are pulsating supergiant stars, massive luminous objects whose outer layers expand and contract on timescales of days to weeks, producing brightness variations that follow a characteristic pattern. RR Lyrae stars are older, less luminous pulsating stars found predominantly in globular clusters, and the halo, with shorter pulsation periods typically measured in hours. What makes both of these types invaluable to astronomy is a relationship discovered in the early 20th century by Henrietta Swan Leavitt, the period luminosity relation. For Cepheids, and analogously for RR Lyrae stars, there exists a tight and well-calibrated correlation between the period of a star's pulsation and its intrinsic luminosity. A Cepheid that takes 10 days to complete one brightness cycle is intrinsically more luminous than one that takes 5 days, by a predictable and measurable amount. This relationship transforms variable stars into cosmic distance indicators of extraordinary utility. By measuring the period of a Cepheid, something that requires only time and a telescope, an astronomer can determine the star's true luminosity. Comparing this true luminosity to the star's apparent brightness as seen from Earth immediately yields the distance through the straightforward relationship between luminosity, apparent brightness, and the square of the distance. Using Cepheids and RR Lyrae stars, astronomers have mapped distances throughout the Milky Way and to nearby galaxies, constructing the framework of distances upon which our entire understanding of the cosmic scale is built. These quietly pulsating stars, expanding and contracting in the dark, far from any observer, are the rulers with which we measure the galaxy. Stars born when the universe was very young, before successive generations of supernovae had time to enrich the interstellar medium, contain almost nothing heavier than hydrogen and helium. For most of the history of astronomy, our knowledge of the Milky Way's three-dimensional structure was severely limited by the difficulty of measuring stellar distances with precision. A star's position on the sky, its right ascension and declination, the two coordinates that tell us where it lies in the celestial sphere, can be measured from the ground with great accuracy. But the third dimension, how far away the star actually is, has always been far harder to determine, requiring specialized techniques, careful calibration, and significant observational effort for each individual measurement. The Gaia spacecraft, launched by the European Space Agency in 2013 and conducting its survey from a stable orbit around the second Lagrange point of the Earth-Sun system, has transformed this situation fundamentally. By measuring the tiny apparent shift in the position of each star as the Earth moves around the Sun, a shift called parallax, whose magnitude is inversely proportional to the star's distance, Gaia has determined precise distances for more than 1 billion stars simultaneously, with a precision and consistency that no ground-based program could approach. The results have been revelatory. Gaia data has revealed the three-dimensional structure of the Milky Way's disk in unprecedented detail, tracing the warp of the outer disk with precision not previously achievable, mapping the distribution of young stars and star-forming regions along the spiral arms, and charting the orbits of millions of halo stars with enough accuracy to identify stellar streams, ancient merger remnants, and kinematically distinct populations that ground-based surveys had only hinted at. The mission has also provided the precise proper motions, the tiny, slow drifts of stars across the sky over time, for an enormous fraction of the galaxy's stellar population, making it possible to reconstruct not just where stars are, but where they are going, and in many cases, where they have been. Successive data releases from the Gaia mission have each produced a cascade of new discoveries and revised understanding. These differences are not subtle. They are measurable with precision using spectroscopy, the technique of splitting starlight into its component wavelengths and reading what is there. The picture of the Milky Way that emerges from this data is richer, more complex, and more dynamic than anything previous generations of astronomers could have assembled. It is, quite simply, the most detailed and comprehensive map of our galaxy ever made, and it is still being refined as new data releases continue to extend and deepen its reach. On a clear night, far from the interference of artificial light, the Milky Way reveals itself as a band of soft luminosity stretching across the sky from horizon to horizon, broader and brighter in some directions, narrower and fainter in others. Its light the collective glow of billions of stars too distant and too numerous to resolve individually. This band is the galactic plane, and it is the densest, most active, most structurally complex region of the entire galaxy. The galactic plane is not a line. It is a volume, a flattened layer of space perhaps 1,000 light-years thick at our location, within which the vast majority of the Milky Way's stars, gas clouds, stellar nurseries, and young star clusters are concentrated. The density of stars in this layer is enormously higher than in the halo above and below it, and the density of gas and dust, the raw material of ongoing star formation, is higher still. It is here, within this crowded and chemically rich environment, that the galaxy's current generation of star formation is primarily occurring. The spiral arms that we move through as we orbit the galactic center are features of the plane, density enhancements within this already dense layer that compress gas and trigger stellar birth on a continuous basis. The stellar nurseries that illuminate those arms, the young open clusters that mark recent sites of star formation, the supernova remnants that record the deaths of the most massive of those newly born stars, all are concentrated in the plane. By analyzing these chemical fingerprints, astronomers can do something remarkable. When we look along the galactic plane on a dark night, we are looking through the maximum depth of the galaxy's disk, peering along the grain of the structure rather than across it. The light we see is the accumulated glow of stars at distances ranging from hundreds to tens of thousands of light-years, layered one behind another until the dust that pervades the plane absorbs and scatters the light from the most distant, leaving us with the soft, diffuse luminosity that ancient observers named after milk. It is the most densely inhabited region of our galactic home, and we can see only the nearest, least obscured portion of it. In the direction of the constellation Sagittarius, low in the southern sky, as seen from most of the northern hemisphere during summer evenings, lies the heart of the Milky Way. The galactic center, the most densely populated, most energetically active, and most gravitationally intense region of the entire galaxy. We cannot see it directly in visible light. Between us and the galactic center lie roughly 26,000 light-years of interstellar space, and within that space, the spiral arms and their associated dust clouds absorb and scatter visible light so thoroughly that the central regions of the galaxy are completely opaque to optical observation. Not a single photon of visible light from the galactic core has ever reached a telescope on Earth. They can group stars into families based on shared origin. The center is, in the optical sense, invisible, and yet it makes its presence felt. Even in the region of the sky where Sagittarius lies, the density of stars is visibly higher than in most other directions. The overlapping light of billions of stars in the inner disk and bulge, producing a noticeably brighter and more densely textured region of the band. In infrared light which penetrates the dust more effectively, the central bulge glows brilliantly, a bright, elongated concentration of ancient stars, marking the location of the galactic core and the peanut-shaped bar that surrounds it. In radio waves and X-rays, the center reveals itself further still. The position of Sagittarius A star, the central supermassive black hole, marked by specific radio and X-ray emissions that no other known object in that region could produce. Surrounding it, within a few light years, is one of the most remarkable stellar environments in the galaxy. A dense cluster of young, massive stars orbiting the black hole at close range. Their presence there a mystery that current theories of star formation struggle to explain. The galactic center is not merely the middle of the Milky Way in a geometric sense. It is the galaxy's engine, the site of its most extreme physics, its greatest gravitational power, and the echoes of its most violent past. We orbit it from our quiet distance, glimpsing it only in wavelengths our eyes were never built to see. Every image of the Milky Way that shows it as a complete spiral, a grand structure viewed from above, its arms curving away from the center in the familiar pinwheel pattern, is, strictly speaking, an artist's impression. They can identify stars that were born in galaxies the Milky Way later consumed. No human instrument has ever photographed the Milky Way from outside. No probe has ever traveled far enough to look back and see the full structure. Every image of this kind is a reconstruction, assembled from measurements, made from within, interpreted through models, and rendered into a form that we can comprehend but have never directly observed. We live inside the galaxy, embedded within its disk, roughly 2/3 of the way from the center to the outer edge, orbiting the galactic center on a path that takes us through the Orion Spur, the minor arm structure we inhabit, and occasionally into the denser regions of the major arms beyond. From this position, looking outward in any direction within the plane of the disk, we see stars layered upon stars, a depth of stellar population that our eyes compress into a flat projection on the sky. What we see when we look at the Milky Way is not the galaxy's shape. It is the galaxy's interior, the view from within a vast three-dimensional structure projected onto the two-dimensional screen of the celestial sphere. The familiar band of light that crosses the sky is the disk seen edge-on from inside, its true spiral structure entirely concealed by our perspective. It took centuries of cumulative observation, mapping stellar distances, measuring gas velocities, tracing the distribution of star-forming regions across the sky, to establish that we inhabit a spiral galaxy and to determine even approximately where within that spiral we are located. They can trace the history of star formation in different regions across different eras. The shape of our own home was one of the last things we were able to see, precisely because we have never been able to step outside it and look back. We know the Milky Way as well as anyone who has ever lived inside a building their entire life can know its exterior architecture. Deeply in some ways, and with an irreducible blindness in others. We have traveled far tonight, through the spiral arms and the stellar nurseries that illuminate them, through the ancient halo and the ghostly streams that trace the galaxy's long history of merging and growth, past the sleeping black hole at the center, the pulsars blinking in the dark, the rogue stars racing outward into the intergalactic void, through clouds of organic molecules drifting between the stars, magnetic fields threading the entire disk, neutrinos streaming through everything without pause or acknowledgement. And yet we have barely touched what the galaxy contains. They can, in a very real sense, read the biography of a star in the language of its light. The Milky Way is larger than any instrument we have built can fully survey, darker than any wavelength of light can fully illuminate, more massive than any method of measurement has yet precisely determined. Within its 100 billion stars and the planetary systems that orbit them, within its molecular clouds and its halo and its invisible scaffold of dark matter, lie more unknowns than knowns, more questions than the science of an entire human civilization has yet had time to pose, let alone answer. We do not know the true nature of dark matter. We do not know whether life exists elsewhere in the galaxy or how common it might be. We do not know the precise structure of the spiral arms or the exact mass of the halo or the full history of every merger that shaped the galaxy we inhabit. We do not know what the Fermi bubbles are telling us about the central black hole's past. We do not know how many rogue planets drift through the halo, or whether the oldest halo stars have companions, or what the very first stars in the galaxy looked like from up close. The Milky Way holds far more than we can see. Chemistry becomes a kind of time machine. Not one that carries us backward through time, but one that lets the past speak to us, quietly, in the spectrum of a distant sun. Across the sky, if you had the instruments to see them, you would find faint ribbons of stars stretched in long, graceful arcs. Far more than we can measure. Far more, perhaps, than we will ever fully understand. And that is not a limitation to lament. It is an invitation to continue looking. A reminder that the galaxy above us is not a solved problem, but a living question, still unfolding, still revealing itself, one discovery at a time. And now the journey draws quietly to a close. The stars grow soft behind your thoughts. The spiral arms recede. The dark matter settles into its invisible halo around everything you have heard tonight, and you are left here, warm, still and resting, somewhere within it all. You have moved, gently, through 100 facts about a galaxy that has been turning for more than 13 billion years. You have heard of stellar streams and ancient mergers, of pulsars keeping time in the dark, of cold clouds holding their breath before the first star ignites within them. Not constellations, of a black hole sleeping at the center, of rogue worlds drifting alone, of gold forged in the collision of dead stars and scattered eventually into the ground beneath your feet. None of this is separate from you. You are not a passenger moving through the galaxy. You are part of it, materially, chemically, gravitationally. The iron in your blood was forged in the heart of a star that died before the solar system existed. The calcium in your bones was scattered by a supernova across light years of space before finding its way, through gas cloud and disk and planet and ocean and life, into you. The oxygen filling your lungs right now was produced in stellar interiors across billions of years of galactic history. You are the galaxy, briefly organized. Not clusters, briefly warm and conscious and curious. Resting, tonight, in a quiet corner of a spiral arm, on a small planet orbiting an ordinary star, inside a galaxy so vast that even its nearest edge is tens of thousands of light years away. The galaxy turns on as you sleep. Stars are forming in cold, dark clouds somewhere in the disk. Light is traveling, right now, from sources so distant it left them before the Earth existed. Silent orbits continue, the sun in its long arc, the halo stars in their tilted paths, the globular clusters in their slow and ancient loops. And you are part of all of it. A small warmth in the dark. A brief arrangement of stardust resting in the arms of a galaxy that made you and that carries you, and that will be here long after the particulars of this moment have dissolved into the deep. Sleep well, something older and stranger than either. Dream softly, and know that the galaxy will keep turning while you do. These are stellar streams, the thinly spread remnants of smaller galaxies that wandered too close to the Milky Way and were gradually pulled apart. As a dwarf galaxy falls inward, the gravity of the Milky Way does not act equally on all parts of it. Stars on the near side are pulled more strongly than those on the far side. Over time, this tidal stretching draws the galaxy out into a long thread, smearing its stars across a great arc of sky that traces the path it once traveled. Some of these streams wrap around the galaxy like ghostly halos. Others curve inward toward the core. Each one is a record, a visible scar of a collision that may have occurred billions of years ago, preserved not in stone, but in the slow drift of stars across space. The sky, properly read, is an archive. And these ribbons of light are some of its oldest entries, delicate, patient, and still in motion. If you imagine the Milky Way as a flat, perfectly level disk of stars, a neat cosmic plate spinning in the dark, the reality is somewhat more surprising. Our galaxy does not lie flat. Its disk bends. On one side, the outer regions curve gently upward. On the other, they dip downward. The result is a slow, graceful wave running through the plane of the galaxy, a warp that becomes most pronounced at the edges of the disk, far from the dense central regions where gravity is strongest. For a long time, this distortion was invisible to us, hidden behind the limits of optical observation. It was radio telescopes, instruments that detect the emissions of cold hydrogen gas rather than visible starlight, that first revealed the true shape of the disk's outer reaches, bending away from the plane we had assumed it followed. What causes the warp is still a matter of study. The gravitational influence of nearby satellite galaxies, tugging unevenly on the disk's edges, is one likely contributor. Clumps of dark matter moving through the halo may also play a role, pulling at the disk from below and to the side. Perhaps both are involved, working together across timescales so long that the warp itself slowly rotates, a wave not frozen in place, but moving through the stars like a ripple across the surface of still water. From a distance, the Milky Way would not look like a perfect spiral. It would look like one that is very gently dancing. On the clearest night imaginable, far from any city under a moonless sky, a human being with excellent vision might look up and count a few thousand individual stars. It feels like an ocean of light. It feels like more than the mind can hold. It is almost nothing. The Milky Way contains in excess of 100 billion stars. The few thousand visible to the naked eye represent roughly 0.003% of the total. The rest are hidden from us by distance, by the limits of human vision, and above all by the vast curtains of interstellar dust that weave through the galaxy in clouds and tendrils, absorbing and scattering the light of stars behind them before it can ever reach our eyes. The pale, hazy band that crosses the night sky on dark evenings, the streak of light we call the Milky Way, is not the galaxy. It is a whisper of the galaxy, the innermost, closest slice of a structure so immense that our entire capacity for vision barely grazes its surface. We live surrounded by a river of light so vast that almost all of it remains permanently beyond our sight. The full Milky Way is not something any human eye will ever take in. We see only the suggestion of it, and even that suggestion is enough to stop the breath. It would be natural to imagine the Milky Way's spiral arms as fixed structures, great solid lanes of stars locked in place, sweeping outward from the galactic center like the arms of a pinwheel. But they are not fixed. They are not even made of the same stars from one moment, on a cosmic scale, to the next. The spiral arms are patterns. More specifically, they are density waves, regions of slightly higher gravitational compression that move slowly through the disk at their own speed, independent of the individual stars around them. Stars drift into these regions, slow down as the density increases, and then continue on their way. The arm itself persists, even as the stars within it are constantly changing. The effect is similar to a slow traffic jam on a long road. The jam has a location. It moves gradually, but the individual cars that compose it are always different. From above, the jam looks like a fixed feature of the road. From within, every car passes through and continues on. As stars and gas clouds enter the compressed region of a spiral arm, the increased pressure can trigger the collapse of gas clouds into new stars. The brightest and most massive of these newly born suns illuminate the arm in brilliant blue and white, tracing out the pattern in glowing light. Then they drift on, and new stars form behind them, keeping the arms alight across enormous stretches of time. By the laws of physics as we understood them for most of human history, the Milky Way should not exist in its current form. When astronomers measure the speed at which stars orbit the galactic center, they find something that does not match the predictions of classical gravity. Stars in the outer regions of the galaxy move far too quickly. If the only mass present were the visible stars, gas, and dust we can detect, those outer stars should be moving more slowly, and many should have long since escaped the galaxy's gravitational grip entirely, flung into the dark by their own momentum. And yet they remain. The galaxy holds together. Something is keeping it intact. That something is dark matter, an invisible, as yet unidentified form of mass that neither emits nor reflects light, that does not interact with ordinary matter in any way we can currently measure, except through gravity. Dark matter surrounds the Milky Way in an enormous halo extending far beyond the visible disk, and there is so much of it that it outweighs all the stars, gas, and dust in the galaxy combined many times over. We have never seen dark matter directly. We do not know what it is made of, but its gravitational signature is unmistakable, and without it, the galaxy we call home would not exist. At the very heart of the Milky Way, hidden behind dense clouds of gas and dust that no visible light can penetrate, there is something extraordinary. a single point of gravity so intense that it warps the fabric of space and time around it for vast distances in every direction. It is called Sagittarius A star, a supermassive black hole containing more than 4 million times the mass of our Sun, compressed into a region of space smaller than the orbit of Mercury around it. We cannot photograph it directly in visible light, but we have watched its influence. For decades, astronomers have tracked stars in the innermost regions of the galaxy, stars moving at tremendous speeds, tracing tight, elliptical orbits around a point that emits no light at all. The invisible mass those orbits imply can only be a black hole of enormous scale. Occasionally, clouds of gas or dust drift close enough to be captured, and as they spiral inward, they heat to extreme temperatures, briefly flaring in X-rays before crossing the event horizon and vanishing. These flares are rare. For now, Sagittarius A star is quiet, dormant by the standards of the most active black holes in the universe. But long ago, it may have been something very different. A blazing engine of energy at the galaxy's heart, lighting the spiral from within. That time has passed. Now it waits, silent and immense, conducting the slow gravitational dance of millions of nearby stars. When astronomers turned infrared telescopes toward the central regions of the Milky Way, instruments capable of seeing through the dust that obscures so much of the galactic core, they expected to find a roughly spherical bulge of densely packed old stars. What they found instead was considerably more unusual. The central bulge is not round. Seen from the side, it swells outward at its middle and narrows toward its ends in a shape that has been compared with some precision to a peanut. Or, alternatively, to an X, a three-dimensional crossing of two thickened ridges of stars, oriented symmetrically around the galactic center. This shape is now understood to be the result of the galaxy's central bar, a dense, elongated structure of stars that rotates slowly across the inner disk. Over billions of years of orbital dynamics, the bar has developed an instability that causes it to buckle and puff upward and downward, above and below the plane, producing the characteristic boxy, peanut-shaped profile we observe today. It is not a simple structure, and it is not a static one. The peanut-shaped bulge slowly rotates. Stars within it follow complex looping orbits, and the gravity it exerts shapes the behavior of gas and stars throughout the inner galaxy. The heart of the Milky Way, it turns out, is not a smooth and featureless sphere. It is intricate, asymmetric, and very much alive with motion. The Milky Way's spiral arms are not simply regions where stars happen to be more numerous. They are, more fundamentally, regions where stars are being born. Drifting through the galaxy in enormous quantities are clouds of molecular hydrogen, cold, dark, and dense, interspersed with traces of dust and more complex molecules. These clouds are the raw material of stars, and they are found throughout the disk. But it is when these clouds encounter the compressed region of a spiral arm that something remarkable happens. The increased pressure triggers the clouds to collapse. Gravity takes hold, and from the dark interior of the cloud, new stars begin to form. The most massive stars born in these nurseries burn at extreme temperatures and emit powerful ultraviolet radiation, which illuminates the surrounding gas and causes it to glow. These radiant regions, called H2 regions or emission nebulae, paint the spiral arms in brilliant light. Blues and silvers, pinks and golds. The arms shine not because stars are crowded there, but because stars are being made there. Every curve of light in the galaxy's spiral structure is, in some sense, a line of creation. A place where the cold and the dark are being transformed, slowly and continuously, into something that burns. Beyond the bright flat disk of the Milky Way, beyond the spiral arms and the dense star-forming lanes, lies something far more diffuse and far more ancient. A vast, roughly spherical structure that envelops the entire galaxy like an invisible shroud. This is the galactic halo. It contains stars, but they are spread thin, ancient, dim, and widely separated, orbiting the galactic center on long, slow, tilted paths that carry them high above and far below the plane of the disk. It contains globular clusters, those compact spheres of hundreds of thousands of stars, drifting through the halo on orbits that can take billions of years to complete. And it contains dark matter, enormous quantities of it, in a distribution so vast and so massive that it likely accounts for the majority of the Milky Way's total gravitational influence. The halo is nearly invisible. There are no bright spiral arms here, no stellar nurseries, no active star formation to speak of. Its light is old and faint, but its mass is immense and its importance is fundamental. Without the halo's dark matter, the disk could not maintain the rotation speeds we observe. The galaxy would not hold. The halo also carries within it the evidence of the galaxy's long history. Stellar streams, disrupted clusters, and the scattered stars of long-consumed companions. It is the galaxy's outer memory, dim and quiet, still holding the shape of things that no longer exist. Among the most striking and venerable objects in the Milky Way are its globular clusters, dense, roughly spherical gatherings of stars, each containing anywhere from tens of thousands to several million individual suns, all bound together by their mutual gravity and orbiting the galactic center from the depths of the halo. The Milky Way is known to harbor more than 150 of these clusters. And they are old. Genuinely profoundly old. Many are estimated to be between 10 and 13 billion years of age, older than the disk of the galaxy itself, and in some cases approaching the age of the universe. The stars within them reflect this antiquity. They are predominantly metal-poor, containing very little in the way of iron, calcium, or other elements, forged in stellar interiors and scattered by supernovae. This tells us they formed early, before the interstellar medium had been enriched by many generations of stellar birth and death. Some globular clusters are thought to be the surviving cores of dwarf galaxies that were consumed by the Milky Way long ago, their outer stars stripped away, leaving only the densest inner remnants still intact. In this sense, they may be among the most direct physical links we have to the galaxy's ancient and turbulent past. They drift through the halo in their slow, patient orbits, compact golden spheres, burning quietly in the dark, older than almost everything around them. Long ago, the Milky Way was a far more frenetic place. In its early billions of years, the galaxy blazed with creative energy. Gas was abundant, dense, and cold enough to collapse readily into new stars. Stellar nurseries ignited across the disk in waves. The spiral arms glowed with the fierce blue light of massive young suns forming and dying in rapid succession. That era has passed. Today, the pace of star formation in the Milky Way has slowed considerably. The galaxy is not done producing new stars. It still forms them steadily in the molecular clouds distributed through the disk and along the spiral arms. But the rate is a fraction of what it once was. Much of the available gas has already been incorporated into stars, or has been heated and dispersed by supernovae and stellar winds into forms that resist gravitational collapse. The raw material is thinner now, more spread out, harder to gather. Astronomers believe that star formation in the Milky Way peaked somewhere between 8 and 10 billion years ago and has been declining gradually ever since. The galaxy is not dying. It remains active, luminous, and productive. But it is maturing, settling into a quieter chapter of its long existence, one in which new stars still emerge, but without the urgency and extravagance of its youth. We live in the middle age of a spiral galaxy. Still bright, still forming, but no longer in any hurry. The disk of the Milky Way, the broad, flat, star-rich spiral we most commonly picture when we think of our galaxy, did not appear all at once. It assembled gradually over billions of years as gas cooled and settled into a rotating plane and successive generations of stars formed within it. But some of the stars that now reside in the galaxy are older than the disk itself. These ancient stars are found mostly in the halo and in the thick disk, the older, puffier layer that sits above and below the thinner, denser plane where most star formation occurs today. They formed during an earlier era when the Milky Way was still a loose, largely unstructured cloud of gas and dark matter, slowly drawing itself together under gravity. There were no spiral arms yet, no coherent rotation, just clumps of dense gas collapsing here and there into the first stellar generations. By studying the motions and chemical compositions of these stars, astronomers can peer back into that formative period, before the galaxy had a recognizable shape, before structure had fully emerged from the primordial chaos. These stars did not form in the Milky Way as we know it. They formed in the conditions that preceded it, the raw and unsettled environment from which the galaxy would eventually grow. They are the elders of the galaxy, silent witnesses to its birth, still burning in the dark long after the world they first illuminated has been entirely transformed. The sun moves through space at a speed that is almost impossible to relate to any human experience. Nearly 830,000 kilometers per hour. Fast enough, in principle, to circle the Earth in under 3 minutes. And yet, measured against the scale of the galaxy, even that velocity is humbled into something patient and slow. One complete orbit of the Milky Way, a single lap of the Sun around the galactic center, takes somewhere between 225 and 250 million years. This span of time has a name, a galactic year. And it is a unit of time so vast that it renders our ordinary calendars almost meaningless by comparison. In the time it takes to complete one galactic year, mountain ranges rise and erode. Entire groups of species appear, flourish, and vanish from the fossil record. Continents shift position measurably. The last time the solar system occupied its current location in the galaxy, the supercontinent Pangaea had only just begun to break apart, and the age of the dinosaurs had not yet begun. One galactic year before that, complex animal life had only recently emerged in the oceans of the early Earth. The galactic year is not a unit we can feel or observe. It is something we can only calculate and then contemplate, a timescale that reframes everything we think we know about history and about time itself. The sun is old by human standards, ancient even by the measure of civilization or recorded history. At approximately 6 billion years of age, it has witnessed the formation of the Earth, the emergence of life, the rise and fall of countless species, and the entire span of human existence. And yet, on a galactic scale, it is still relatively young. A newcomer among stars, many of which have been burning far longer. In all of its 6 billion years, the Sun has completed fewer than 25 full orbits of the Milky Way. 20-some laps around a galaxy that has been turning for more than 13 billion years. Stars that formed in the galaxy's earliest epoch have circled the center perhaps 50 or 60 times in the same span. Seasoned travelers compared to our own Sun, which is still, in cosmic terms, early in its journey. There is something quietly humbling in this. We tend to think of the Sun as a fixture, ancient, reliable, essentially permanent. And in human terms it is. But step back far enough, widen the frame enough, and it becomes something else. A relatively young star on a relatively young planet, partway through its first few dozen orbits of a galaxy that was already billions of years old when it formed. We are not late arrivals to the cosmos, but we are not among its elders either. In our own solar system, the planets follow a pattern that Isaac Newton's laws describe with great precision. Mercury, closest to the Sun, moves fastest. Neptune, at the far edge, moves slowest. The relationship between distance and orbital speed is clear, consistent, and mathematically predictable. Astronomers naturally expected to find the same pattern in the Milky Way. Stars closer to the galactic center, where most of the visible mass is concentrated, should orbit quickly. Stars in the outer disk, far from that central concentration of mass, should orbit far more slowly, just as Neptune moves more slowly than Mercury. But when they measured it, they found something else entirely. Stars in the outer regions of the Milky Way orbit nearly as fast as stars much closer to the center. The expected drop-off in orbital speed does not occur. The rotation curve, the graph of orbital speed against distance from the center, stays stubbornly, inexplicably flat. This observation, first made by astronomer Vera Rubin and her colleagues in the 1970s and confirmed many times since, became one of the most important pieces of evidence for the existence of dark matter. If there is an enormous quantity of invisible mass distributed throughout a vast halo surrounding the galaxy, mass that exerts gravitational force without emitting any light, then the flat rotation curve makes sense. The outer stars are not defying gravity. They are responding to mass we simply cannot see. Scattered through the disk of the Milky Way, drifting slowly between the stars, are some of the coldest and darkest places in the known universe. They are not voids. They are clouds, enormous concentrations of molecular hydrogen gas mixed with traces of dust and a remarkable variety of more complex molecules existing at temperatures only a few degrees above absolute zero. These molecular clouds are the galaxy's reserve of raw material, the stockpiles from which future stars will be drawn. Some of them are relatively modest in scale. Others are vast, spanning hundreds of light years across, containing enough mass to eventually produce thousands or even millions of new suns. In visible light, these clouds are invisible or nearly so. They do not glow. They absorb the light of stars behind them, appearing as dark patches against the brighter background of the galaxy. Regions where the stars seem to thin and disappear, not because space is empty there, but because something cold and dense is blocking the view. Within their interiors, where the darkness is most complete and the temperature most extreme, gravity works in silence. Slowly, over vast stretches of time, small regions of higher density begin to attract more material. The collapse begins almost imperceptibly at first. And somewhere inside that cold and lightless cloud, the first stirrings of a future star are already underway. A massive star, one perhaps 10 or 20 times the mass of the Sun, lives fast and dies violently. In only a few million years, it exhausts the nuclear fuel at its core, and when it does, the result is catastrophic. The outer layers of the star collapse inward at tremendous speed, then rebound in an explosion of almost unimaginable energy. A supernova. A single event that can briefly outshine the combined light of every other star in the entire galaxy. These explosions are not merely endings. They are, in a very real sense, the galaxy's most powerful creative force. The shock waves that radiate outward from a supernova can travel for hundreds of light years, compressing gas clouds they encounter and triggering the gravitational collapse that leads to new star formation. In this way, the death of one massive star can directly cause the birth of many others, a chain of creation set in motion by destruction. At the same time, the explosion scatters into the surrounding space all of the heavy elements that the dying star spent its lifetime forging in its core. Iron, silicon, calcium, nickel. Elements that will eventually find their way into new gas clouds, new stars, new planets. The atoms of which the Earth is made, and of which you are made, were distributed across the galaxy in events like these, long before the solar system existed. Supernovae are the storms of the Milky Way, violent and radiant, destructive and necessary. The galaxy would not be what it is without them. The Milky Way is full of light that we will never see with unaided eyes, and full of darkness that is not truly dark at all. Between the stars, woven through the spiral arms and concentrated in the plane of the disk, lies a vast quantity of interstellar dust. Not the household dust of daily life, but something far more exotic. Microscopic grains of carbon, silicates, and ice, each smaller than a wavelength of visible light. Individually insignificant. Collectively, across the immense distances of the galaxy, capable of blocking entire regions of space from view. Where these dust clouds are thickest, visible light cannot pass. Stars behind the cloud are extinguished entirely. Stellar nurseries where new suns are actively forming are rendered completely invisible. To optical telescopes and to human eyes, these regions appear as dark voids, places where the galaxy seems to fall silent. But they are not silent. They are some of the most active places in the galaxy. Infrared light, with its longer wavelengths, passes through interstellar dust with far greater ease than visible light. Infrared telescopes, both ground-based and space-based, including instruments like the Spitzer Space Telescope and the James Webb Space Telescope, can pierce these curtains of dust and illuminate what lies behind them. What they reveal are glittering stellar nurseries, dense and radiant, full of newly forming suns embedded in cocoons of warm gas. What looks from the outside like absence is, from within, abundance. The darkest places in the galaxy are often the most alive. Not every cold gas cloud in the Milky Way collapses into stars. Not every reserve of raw material is ever spent. Across the galaxy, there exist vast clouds of molecular hydrogen, massive enough, cold enough, dense enough, that appear to be on the verge of collapse and yet remain dormant. Dark, still and unchanged across timescales that dwarf human civilization. The reasons for their inactivity are not always clear. Some clouds may be too diffuse, spread thin enough that gravity cannot gain sufficient purchase to begin a meaningful collapse. Others may be threaded through with strong magnetic fields, which can resist the inward pull of gravity and hold a cloud in a state of suspended tension for an extraordinarily long time. Internal turbulence, random motions of the gas within the cloud, can also work against collapse, stirring and disrupting the density fluctuations that gravity needs in order to take hold. These dormant clouds drift through the galaxy like quiet possibilities. They contain everything needed to form stars and, eventually, planets. Perhaps even the conditions for life. And yet they float on, patient and untouched, waiting for a nudge that may or may not ever arrive. A passing shockwave from a distant supernova. A gravitational disturbance from a nearby spiral arm. Some small perturbation sufficient to tip the balance and set the slow, inevitable process of collapse in motion. Until then, they drift, the galaxy holding its breath inside them. Nothing in the Milky Way is truly lost. Matter changes form, changes location, changes temperature, but it does not disappear. The galaxy operates across deep time as a vast recycling engine, and stars are both its primary consumers and its most generous contributors. A star spends its life fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon, carbon into oxygen, and so on up through the periodic table. When it dies, it returns that material to the galaxy. A star like the Sun, at the end of its life, will expand into a red giant and shed its outer layers in a slow, glowing wind, scattering enriched gas into the surrounding space. More massive stars explode as supernovae, distributing their contents violently across hundreds of light-years in moments. This returned material, now richer in heavy elements than the gas from which that star originally formed, mixes with the interstellar medium. It cools. It drifts. It joins other clouds, and eventually, over timescales of millions of years, gravity gathers it once more into new stars, new planetary systems, and potentially new forms of complexity. Every atom in your body has participated in this cycle. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was processed inside one or more previous stars, scattered into space by their deaths, and gathered again into the cloud that eventually formed the solar system. The galaxy does not merely contain life. In a very deep sense, it produces it, recycling its own substance, generation after generation, into ever greater complexity. In the outer halo of the Milky Way, drifting in long, slow orbits far above the plane of the disk, there exist stars of a particular and remarkable kind. They are faint, they are old, and they carry within their atmospheres a chemical record of the universe as it existed in its earliest infancy. These are metal-poor stars, and in the language of astronomy, metal refers to any element heavier than helium. The earliest stars in the universe formed from gas that was almost entirely hydrogen and helium, because those were the only elements produced in significant quantities by the Big Bang itself. Heavier elements, carbon, oxygen, iron, and all the rest, had to be forged inside stars and then scattered by their deaths. That process takes time, and the most ancient stars formed before it had proceeded very far. By seeking out and analyzing these metal-poor stars in the halo, astronomers gain access to a window that cannot be opened any other way. The chemical composition of a metal-poor star reflects the state of the interstellar medium at the time and place it was born, a snapshot of conditions in the early universe, preserved across billions of years in the spectrum of a still-burning sun. Some of these stars contain so little in the way of heavy elements that they appear to preserve the chemistry of the very first supernovae, the explosions of the universe's first generation of massive stars, events that took place more than 13 billion years ago. They are fossils made of light, and they are still burning. A star is born in a particular place, a specific region of a specific molecular cloud, in a specific part of the galaxy at a specific moment in time. But that birthplace is rarely where the star spends the rest of its life. Over time, most stars drift. Some drift gradually. Others are displaced dramatically. And a few are flung so far from their origins that no trace of the journey remains. The causes of stellar migration are varied. Gravitational interactions with nearby stars can nudge an orbit slightly inward or outward. The passage of a spiral density wave can exchange angular momentum with a star, shifting its orbital radius in ways that accumulate across billions of years. Close encounters with massive molecular clouds can deflect a star's path entirely. And in extreme cases, as we have already seen, interactions near the galactic center or within dense clusters can hurl a star outward at tremendous speed. Even our own sun is almost certainly not where it began. Current models suggest that the sun may have formed somewhat closer to the galactic center than its present position, and migrated outward over billions of years to the orbit it follows today. The neighborhood it was born in, whatever stellar siblings surrounded it in those first millions of years, is long gone, scattered and dispersed across regions of the galaxy we have not yet identified. A star's origin does not define its path. The galaxy is not a fixed address. It is a slowly shifting current, and even the most stable-seeming stars are, on long enough timescales, travelers. Just as Earth occupies a particular range of distances from the Sun, close enough to be warm, far enough to avoid being scorched, the Milky Way itself may have a region particularly well suited to the emergence of life. A galactic habitable zone, defined not by temperature alone, but by a more complex balance of conditions. The inner regions of the galaxy, close to the dense and turbulent core, are hostile to life in ways that have nothing to do with warmth. Stellar density is high, meaning gravitational disruptions to planetary orbits are more frequent. Supernovae occur more often, bathing nearby systems in lethal doses of radiation. The central black hole, during its more active phases, may have periodically flooded the surrounding galaxy with high-energy outbursts capable of stripping away atmospheres and sterilizing planetary surfaces. The outermost regions of the galaxy present a different problem. Here, the density of heavier elements, the raw material from which rocky planets and the chemistry of life are built, drops sharply. Stars in the outer disk and halo formed from gas that had been enriched far less by previous stellar generations, and the planets that form around them may lack the elemental complexity that life, as we understand it, requires. Between these two extremes lies a broad intermediate band, a region where stellar density is moderate, heavy elements are abundant, supernovae are neither too rare nor too frequent, and gravitational conditions are relatively stable. Earth lies within this zone, and it raises a quiet question. How many other worlds in this same band of possibility might have arrived at the same fortunate balance? We have touched on the nature of spiral arms before, that they are density waves rather than fixed structures, patterns rather than permanent features. But the full picture of how these arms sustain themselves across billions of years is worth dwelling on, because it is one of the more elegant processes in all of galactic astronomy. As a wave of higher density moves slowly through the disk, it compresses the gas and dust in its path. This compression triggers star formation. The most massive stars born in these events burn hot and bright, but briefly. They live for only a few million years before exhausting their fuel and exploding. During their short lives, they illuminate the spiral arm in vivid blue and white, making it visible across enormous distances. When they die, they enrich the surrounding gas with heavy elements, and their shockwaves can trigger further star formation, the next generation already beginning to ignite as the previous one burns out. Meanwhile, less massive stars drift out of the arm on their slower, quieter orbits, entering the interarm regions where the density drops and star formation largely ceases. The arm itself moves on, compressing new material, triggering new stars, maintaining its shape through the same process indefinitely. It is a self-sustaining wave of creation, not a structure built once and preserved, but a pattern continuously renewed by the very processes it initiates. From far enough away, it looks like a fixed and graceful curve of light. From within, it is something far more dynamic, a slow fire that moves through the galaxy, never consuming the same fuel twice. When we look at the night sky, we are seeing only one narrow band of the full electromagnetic spectrum. Visible light, the light our eyes evolved to detect, represents a tiny fraction of the radiation that fills the universe. And the Milky Way, seen in its full breadth across all wavelengths, is a far stranger and more violent place than the serene canopy of stars above us suggests. In X-rays, the galaxy blazes with the light of extreme heat. Collapsed stellar remnants, neutron stars and black holes in binary systems draw matter from companion stars, accelerating it to enormous velocities and heating it to temperatures of millions of degrees before it falls inward. This process radiates intensely in X-rays, visible to space-based observatories, but entirely invisible to human eyes. In gamma rays, the most energetic form of light, the galaxy reveals a different kind of violence. Pulsars, supernovae remnants, and the region around the central black hole all contribute to a gamma-ray glow that maps a galaxy of extreme energetics beneath the calm optical surface. In radio waves, cold hydrogen gas traces the spiral arms, the warp of the disk, and the outer reaches of the galaxy far beyond what starlight reveals. And threading through all of it, cosmic rays, high-energy charged particles moving at close to the speed of light, stream through the galaxy in every direction, carrying energy and information from some of its most violent events. The Milky Way is not one galaxy. It is many, depending on the wavelength through which you choose to look. In 2010, astronomers analyzing data from the Fermi Gamma Ray Space Telescope made a discovery that no existing model of the galaxy had predicted. Extending from the galactic center, upward and downward, above and below the plane of the disk, were two enormous structures glowing in gamma rays, each one stretching approximately 25,000 light-years from the center. Together they form a shape reminiscent of two vast balloons, inflated back-to-back, or a single hourglass of high-energy light standing perpendicular to the galactic plane. These became known as the Fermi bubbles, and they remain one of the most intriguing and debated features of the Milky Way. What created them is not yet settled. One leading hypothesis holds that they are the remnant of a period of intense activity from Sagittarius A star, the central black hole, during which it consumed large quantities of gas and radiated enormous amounts of energy outward, inflating these lobes of hot, high-energy plasma over millions of years. Another possibility is that they were produced by a period of exceptionally vigorous star formation near the galactic center, with the combined winds and supernovae of many massive stars driving material upward in a powerful outflow. Either way, the Fermi bubbles are a reminder that the Milky Way carries within it the echoes of events far more dramatic than anything occurring today. Great eruptions from its past, written in high-energy light, hovering silently above and below the stars we know. Our solar system does not reside in one of the Milky Way's grand luminous spiral arms, those brilliant arcs of young stars and active star formation that define the galaxy's most visually dramatic regions. Instead, we occupy a far more modest address. We are located in a structure called the Orion Spur, sometimes also called the Orion Arm or the Local Arm, a relatively short, partial arm or spur of stars that bridges the space between two of the galaxy's larger arms, the Sagittarius Arm on the inner side and the Perseus Arm further out. It is not especially dense. It is not especially active. By the standards of the galaxy's most productive regions, it is quiet. And that quietness may be significant. In the denser, more active regions of the spiral arms, massive stars form and die in greater numbers, producing supernovae more frequently. These explosions release intense radiation that can be harmful to complex chemistry and potentially to life. Gravitational disturbances are more common in crowded stellar neighborhoods, and the risk of orbital disruptions to planetary systems is correspondingly higher. In the calmer interarm region where we find ourselves, these hazards are reduced. Supernovae are rarer. Gravitational perturbations are less frequent. There is more stability, and stability sustained over billions of years may be precisely what biological complexity requires in order to arise and persist. We did not choose this address, but it may be, in more ways than one, that the quietness of our corner of the galaxy is part of what made us possible. Look toward the center of the Milky Way in infrared light, the wavelength that penetrates the dust clouds, obscuring our view in visible light, and the galaxy reveals a feature that sets it apart from the simplest spiral forms. Crossing the central region, oriented at an angle to the main spiral arms, is a thick and elongated structure of densely packed stars. Not a circular bulge, but a bar, an extended rotating bridge of stellar mass that cuts across the galactic center. This central bar spans roughly 27,000 light-years from end to end, and it rotates slowly as a coherent structure, completing a rotation on a timescale of hundreds of millions of years. As it turns, its gravity acts on the surrounding gas and stars in ways that have profound consequences for the entire inner galaxy. The bar channels gas inward along specific gravitational pathways, funneling material toward the central regions and occasionally feeding the supermassive black hole at the core. It drives the formation of what are called resonance rings, circular concentrations of gas and stars that form at specific distances from the center where the bar's gravitational influence is particularly strong. And it shapes the inner ends of the spiral arms, which appear to emerge from the tips of the bar rather than from the galactic center directly. Barred spirals like the Milky Way are in fact the most common type of spiral galaxy in the universe. The bar is not an anomaly. It is, it seems, the natural outcome of how disk galaxies evolve, a structure that forms spontaneously from the orbital dynamics of billions of stars and then reshapes everything around it. The Milky Way does not exist in isolation. It is not an island in an otherwise empty cosmos. It is a member of a community, a gravitationally bound collection of galaxies known as the Local Group, which spans a region of space more than 10 million light-years across and contains more than 50 individual galaxies of varying sizes, types, and compositions. The two dominant members of the Local Group are the Milky Way and the Andromeda Galaxy, two large spiral galaxies of broadly comparable mass, each with its own retinue of smaller companions. Around the Milky Way orbit a number of dwarf satellite galaxies, including the Magellanic Clouds visible from the southern hemisphere and numerous smaller, fainter systems. Andromeda has its own attendants as well. The remaining members of the Local Group are mostly small, dwarf ellipticals, dwarf irregulars, and in some cases extremely faint galaxies composed almost entirely of dark matter, with only a handful of visible stars to mark their presence. These small members are scattered through the group in no particular order, some orbiting the two giants, others drifting more independently through the shared gravitational field. The Local Group itself is part of an even larger structure, the Virgo supercluster, and beyond that, the Laniakea supercluster, a vast cosmic web of galaxies spanning hundreds of millions of light-years. But at the scale of our immediate neighborhood, the Local Group is home. A quiet gathering of galaxies, bound together by gravity, drifting through the universe as a unit. The universe as a whole is expanding. Galaxies far beyond our Local Group are receding from us, carried outward by the stretching of space itself, their light shifted toward the red end of the spectrum by the increasing distance between us and them. On the largest scales, the cosmos is growing and will continue to grow forever. But within the Local Group, a different dynamic operates. Here, gravity is strong enough to overcome the expansion of space. The galaxies of the Local Group are not receding from one another. They are bound together in a shared gravitational embrace, and many are moving closer. The most dramatic example is the approach of Andromeda, but it is not alone. Many of the smaller members of the Local Group are also in motion relative to one another, their paths curved by the gravity of their neighbors, their trajectories slowly converging or looping in long orbital arcs that play out over billions of years. Over immense timescales, the Local Group may gradually condense. Smaller galaxies will be absorbed by the two giants. The two giants will eventually merge. What remains, billions of years from now, may be a single large elliptical galaxy, sometimes called Milkomeda by astronomers, sitting alone in a region of space increasingly empty as the rest of the universe recedes beyond the horizon of visibility. The Local Group is not falling apart. It is, slowly and patiently, drawing itself together. A family not dispersing but converging, bound by the same force that holds galaxies together, holds stars in their orbits, and holds you tonight gently to the Earth. Look at the Milky Way's disk not as a single flat structure, but as something layered. And what you find is a record of the galaxy's history, written in the distribution of stars across different heights above and below the galactic plane. The thin disk is where we live. It is roughly 1,000 light-years thick, and it contains the youngest stars, the most active star-forming regions, the open clusters of newly born suns, and the densest concentrations of gas and dust. It is the Milky Way at its most current, the active, productive surface layer of galactic life. Above and below the thin disk, extending to thicknesses several times greater, lies the thick disk. It is older and more diffuse. Its stars are predominantly ancient, many billions of years old, with lower abundances of heavy elements than their counterparts in the thin disk, reflecting the less enriched state of the galaxy at the time they formed. Their orbits are more tilted and more elliptical, carrying them higher above and below the plane than the more orderly paths of the thin disk's inhabitants. The thick disk is thought to have formed during a period of significant disruption early in the galaxy's history, possibly stirred into its current puffier configuration by the impact of a large infalling galaxy that disturbed and heated the stars of the then thin disk, thickening and disordering it. What had been flat became layered. What had been uniform became textured. The disk we move through today is not a single thing. It is a geological record, strata of stellar generations, each laid down in different conditions, each telling a slightly different part of the same long story. The Milky Way is pervaded by a force that no human eye can see and no human body can feel, and yet it shapes the behavior of matter across the entire disk, the halo, and the vast reaches of the interstellar medium in between. The galaxy possesses a magnetic field, not a strong one by the standards of what we encounter on Earth or near the surface of a neutron star, but strong enough across galactic distances to exert a profound and pervasive influence. This magnetic field is not uniform. It follows the broad sweep of the spiral arms, winding through the disk in coherent patterns that align broadly with the rotation of the galaxy. But it also twists and loops in more complex ways, rising above the plane in arcs, diving back down in filaments, forming large-scale structures in the halo that we are still working to map and understand. The consequences of this field are far-reaching. Cosmic rays, charged particles, cannot travel in straight lines through a magnetized medium. They spiral along field lines, bounce between magnetic irregularities, and are deflected and scattered as they propagate through the galaxy. The distribution and energy of cosmic rays throughout the Milky Way is shaped in large part by its magnetic structure. Gas clouds, too, are influenced by the magnetic field. In regions where the field is strong, it can resist the gravitational collapse of a cloud, delaying or preventing star formation. Dust grains align with field lines, polarizing the starlight that passes through them and leaving a subtle signature that astronomers use to trace the field's orientation across vast distances. The Milky Way does not merely glow with light. It is threaded throughout its entire extent with invisible lines of magnetic force, a quiet architecture of fields woven into the fabric of the galaxy itself. It is tempting to think of the space between stars as nothing, as pure void, featureless and inert, a backdrop against which the real content of the galaxy plays out. But the interstellar medium, as astronomers call it, is anything but nothing. It is a complex, structured and actively dynamic environment that plays a central role in virtually every process that shapes the Milky Way. The interstellar medium is composed of gas in several distinct phases. There is hot, diffuse gas, plasma heated to millions of degrees by supernova shockwaves, glowing faintly in X-rays and occupying enormous volumes carved out of the disk. There is warm gas at intermediate temperatures, neither hot enough to be fully ionized nor cold enough to form molecules. And there are cold, dense clouds, the molecular clouds we have already discussed, where temperatures drop near absolute zero and complex chemistry becomes possible. These phases are not static. They interact continuously, exchanging mass and energy as shockwaves from supernovae expand into warm gas, as gas cools and condenses into clouds, as stellar radiation ionizes the edges of those clouds and keeps them in a state of ongoing transformation. The interstellar medium is, in a very real sense, in a state of constant flux. Woven through it all are magnetic fields, streams of cosmic rays, and flows of material driven by stellar winds and supernova explosions. At every scale, from individual star-forming clumps to the broad sweep of spiral arms, the interstellar medium is structured, turbulent, and deeply engaged in the processes that make the galaxy what it is. The space between stars is not empty. It is where much of the galaxy's life takes place. Every second of every day, your body is traversed by particles from across the galaxy. You cannot feel them. They leave no sensation as they pass through skin and bone and organ. And yet they are there, streaming downward through the atmosphere, penetrating the Earth itself, passing through you and continuing onward without pause or deflection. These are cosmic rays. Not rays in the electromagnetic sense, not light of any wavelength, but high-energy charged particles, mostly protons and atomic nuclei, accelerated to enormous velocities by some of the most violent events the galaxy produces. Supernovae are the primary suspects. The shock waves from stellar explosions are capable of accelerating particles to energies that no human-built accelerator has yet matched, flinging them into the interstellar medium at speeds approaching that of light. Once launched, cosmic rays travel through the galaxy over vast distances and timescales. They do not travel in straight lines. The galaxy's magnetic field bends their paths, causing them to spiral and scatter across the disk and halo. By the time they reach Earth, the particles have typically traveled for millions of years and crossed distances of thousands of light years, their original trajectories long lost. When they strike the upper atmosphere, they collide with atoms and produce cascades of secondary particles, muons, pions, electrons, that rain down through the air to ground level and below. Some penetrate deep into the Earth. A few are captured by detectors buried in ice sheets or deep underground, where physicists study them for clues about the distant violent events that set them in motion. The galaxy reaches down to touch us every second in particles too small and too swift to notice. In diagrams and illustrations, the Milky Way is almost always shown as a thing of symmetry. A balanced, elegant spiral with matching arms curving away from a centered core. The same above the plane as below, the same on one side as the other. It is a useful approximation, but it is, in important ways, incorrect. The real Milky Way is lopsided. Not dramatically so, not in a way that would be immediately obvious to a distant observer, but measurably and in several distinct respects simultaneously. The disk itself is not equally thick on all sides. One region of the outer disk rises more prominently above the plane than the opposite side dips below it. The spiral arms are uneven in their extent, their brightness, and their degree of definition. Some are longer and more clearly structured than others, and they do not emerge from the center in perfectly matched pairs. Even the stellar halo, the diffuse outer envelope of ancient stars surrounding the disk, appears to be slightly off-center relative to the galactic core. These asymmetries are not random imperfections. They are the accumulated record of the galaxy's history. The gravitational influence of the Magellanic Clouds tugging on the outer disk, the effects of ancient mergers that disturbed the halo's distribution, the ongoing interactions with dark matter clumps that move through the surrounding medium. Each asymmetry is a signature. Each lopsided feature points back toward a cause, an event, a history that shaped the galaxy into something more interesting and more honestly complex than any idealized diagram suggests. The Milky Way is not perfectly balanced. It carries its past in its shape. In the outer halo of the Milky Way, far above the plane of the disk, there drifts a star so ancient that its existence approaches the very boundary of what is cosmologically possible. It is faint, a dim red star, low in luminosity, burning slowly and quietly on a timescale far longer than more massive suns. Its orbit is long and tilted, carrying it high above the galactic plane on a path that bears no particular relation to the orderly rotation of the disk below. And its chemistry is, by the standards of the stars we know best, almost shockingly sparse. The atmosphere of this star contains almost none of the heavy elements that younger stars carry in abundance. Almost no iron, almost no calcium, none of the enriched material that successive generations of stellar death scatter into the interstellar medium. What it does contain is almost pure hydrogen and helium, with only the faintest traces of elements beyond. This chemical signature dates it. It places its formation in the very earliest period of the universe, more than 13 billion years ago, at a time when the cosmos was less than a billion years old. The Milky Way itself had not yet fully formed. The structures we think of as defining our galaxy, the disk, the spiral arms, the bar, did not yet exist. Whatever loose assembly of gas and dark matter preceded the galaxy we know, this star formed within it, or perhaps within a smaller system that was later absorbed. It has been burning ever since. Through the entire history of the galaxy, through the formation of the sun, the earth, the emergence of life, it burns still, quietly, in the dark above the plane. Not all parts of the Milky Way move at the same pace. The galaxy does not rotate as a rigid body. It is not like a spinning plate, where every point on the surface completes a full rotation in the same amount of time. Instead, different regions of the galaxy orbit the center at different rates, and the relationship between distance and orbital period is one of the defining characteristics of galactic dynamics. Near the galactic center, where the concentration of mass is greatest, packed with billions of old stars in the central bulge, dense gas clouds, and the immense gravitational influence of Sagittarius A star, stars complete their orbits with remarkable speed. Some of the stars in the very innermost regions orbit the central black hole in periods of only a few years. Others, slightly farther out but still well within the inner galaxy, complete full circuits in millions of years, rather than hundreds of millions. The Sun, at its distance of roughly 26,000 light-years from the center, takes between 225 and 250 million years per orbit, a timescale that makes even geological epochs seem brief. Stars in the outermost disk, tens of thousands of light-years farther still, take longer still, their paths so vast and their velocities, though surprisingly high thanks to dark matter, insufficient to dramatically shorten the journey. This differential rotation, this uneven turning of the galaxy at different speeds across its extent, is not merely an interesting detail. It is one of the primary mechanisms by which spiral arms are generated and maintained, by which the interstellar medium is stirred, and by which the overall structure of the disk is shaped and reshaped across cosmic time. The galaxy moves like a great fluid, each part flowing at its own rate, the whole remaining coherent through gravity's patient orchestration. The spiral arms of the Milky Way have persisted for billions of years. This is, on reflection, a remarkable fact, because the arms are not solid structures and the stars within them are not locked in place. If the arms were simply regions where stars happen to be clustered, differential rotation would long ago have wound them into indistinct smears. The inner stars move faster, the outer stars move slower, and over hundreds of millions of years, any fixed pattern would be stretched and erased. And yet the arms remain. They are self-sustaining, and the mechanism by which they sustain themselves is one of the more elegant in galactic astronomy. As the density wave of a spiral arm moves through the disk, it compresses gas and dust, triggering the formation of new stars. The most massive of these stars burn brilliantly for only a few million years, brief lives by stellar standards, before exploding as supernovae. These explosions release energy into the surrounding gas, and their shock waves can compress adjacent material, potentially triggering yet another wave of star formation ahead of the arm's advancing edge. The ultraviolet radiation from massive young stars ionizes nearby gas clouds, causing them to glow in the characteristic pinks and reds of emission nebulae, the most visually striking features of any spiral galaxy viewed from outside. These glowing regions trace the arm's leading edge, making it visible across millions of light-years. Meanwhile, the energy released by dying stars helps maintain the pressure differential that defines the density wave in the first place. The arm, in a sense, generates the conditions for its own continuation. It is a pattern that perpetuates itself through the very processes it initiates, a self-renewing structure written in starlight and sustained by stellar death. It begins in a place of extraordinary stillness. A molecular cloud, one of those vast cold reservoirs of gas we have discussed, drifting slowly through the galaxy, its interior chilled to within a few degrees of absolute zero. No starlight penetrates its densest regions. No warmth reaches its heart. It is, in the most literal sense, dark and cold and quiet. And yet, within that darkness, something is happening. Very slowly, almost imperceptibly, gravity is at work. In a region of the cloud where the density is slightly higher than average, perhaps due to the passage of a density wave, perhaps due to the shock from a distant supernova, perhaps simply due to chance fluctuations in the gas, the inward pull of gravity begins to outweigh the outward pressure of the gas. The cloud begins to collapse. Slowly at first, then faster as the density increases and gravity strengthens. As the gas falls inward, it heats. The cloud fragments into smaller clumps, each collapsing on its own trajectory, each destined to become a star or a system of stars. At the center of each fragment, a protostar forms, a dense, hot, still accreting body of gas that has not yet ignited nuclear fusion. Around it, the remaining gas and dust settle into a rotating disk, the same disk from which, over millions of years, planets will eventually form. Then, when the temperature and pressure at the protostar's core reach the extraordinary threshold required to fuse hydrogen into helium, fusion ignites. A star is born. Light pours outward for the first time. The surrounding gas begins to glow and disperse. From the coldest darkness, the brightest light. The process that has filled the galaxy with stars, repeated across billions of years, in cloud after cloud, in arm after arm, always beginning the same way, in silence and cold, and ending in fire. Stars are rarely born alone. The conditions that produce one star, a sufficiently dense, sufficiently massive region of a collapsing gas cloud, typically produce many. A single large molecular cloud, fragmenting under gravity, may give rise to hundreds or thousands of stars in a relatively short period of time, all forming in the same region of space from the same reservoir of gas. These groups are called open clusters, and they begin their lives as compact, coherent families of stars moving together through the galaxy. But they do not stay together. The forces that would hold a cluster intact indefinitely are, over long timescales, insufficient to overcome the many disruptions the galaxy provides. The tidal field of the Milky Way itself, the differential gravitational pull exerted on the near and far sides of a cluster by the mass of the galaxy, slowly stretches and distorts the cluster's shape, peeling stars away from the edges over millions of years. Close encounters with other stars or with massive molecular clouds can scatter members with gravitational kicks. And the internal dynamics of the cluster, the complex gravitational dance of hundreds of stars interacting with one another, naturally cause the occasional member to reach escape velocity and drift away. Star by star, over timescales of hundreds of millions to billions of years, the cluster dissolves. Its stars join the general field of the galaxy, indistinguishable from their neighbors, their shared origin preserved only in their similar ages, similar compositions, and, if traced carefully enough, similar motions through the disk. Our own sun was almost certainly born in such a cluster. Its siblings are out there somewhere, scattered across the galaxy, their common ancestry still written faintly in their chemistry and their orbits, waiting perhaps to be found. Among the most scientifically precious objects in the Milky Way are stars so extremely deficient in heavy elements that they occupy a category of their own, a tier of antiquity beyond even the ordinary metal-poor stars of the halo. These are called hypermetal-poor stars, and they are among the oldest individual objects known to exist anywhere in the universe. Where a typical old halo star might contain a few percent of the iron abundance found in the Sun, hypermetal-poor stars contain 100,000 times less, or in some cases even less than that. Their atmospheres are composed almost entirely of hydrogen and helium, with only the faintest chemical whisper of anything heavier. Some appear to carry the signature of enrichment by a single supernova, as if, in the environment where they formed, only one or a very few massive stars had yet lived and died, leaving behind just the thinnest dusting of heavier elements before the next generation of stars condensed from the enriched gas. These stars are extraordinarily rare. Decades of systematic surveys of the halo, examining millions of stars for the telltale spectral signatures of extreme metal poverty, have turned up only a handful of genuine hypermetal-poor stars. Each one is treated as a discovery of the first order, an object worthy of intense and sustained study. They are lanterns from the dawn of cosmic time, each one burning quietly in the halo, carrying within its ancient light a message from an era so remote that even the galaxy itself had not yet fully come into being. To find them is to reach back, almost, to the very beginning. For most of human history, the question of whether other planets existed beyond our solar system was purely philosophical, a matter of speculation rather than observation. We had no means of detecting them, no way of knowing whether the formation of worlds around a star was a rare accident or a routine consequence of stellar birth. The answer, it has now become clear, is the latter. Planets are not rare. They are a natural and almost inevitable product of the same process that forms stars. When a molecular cloud collapses and a protostar ignites at its center, the surrounding gas and dust do not simply disperse. Conservation of angular momentum, the same principle that causes a spinning skater to accelerate when drawing in their arms, causes the infalling material to flatten into a rotating disk around the young star. Within this protoplanetary disk, particles collide and stick together. Dust grains accumulate into pebbles. Pebbles accumulate into boulders. Boulders accumulate into planetesimals, the embryonic building blocks of planets. And over millions of years, planetesimals collide, merge, and grow into worlds. This process occurs wherever stars form. Surveys conducted by space telescopes, including Kepler, TESS, and others, have revealed that planets are extraordinarily common throughout the Milky Way. Most stars appear to host at least one planet. Many host several. The galaxy almost certainly contains more planets than stars, perhaps several times more. Some of these worlds are vast gas giants. Others are dense and rocky. Some orbit in the habitable zones of their stars at distances where liquid water might persist on their surfaces. The Milky Way is not simply full of stars. It is full of worlds, billions upon billions of them, each one the product of the same quiet, inevitable process of collapse and accumulation. The Sun moves through the Milky Way at its own speed, following its own orbit around the galactic center. The spiral arms of the galaxy rotate at their own speed, slower than the stars in the inner disk, faster than those in the outer reaches. And at a specific distance from the galactic center, there exists a radius at which these two speeds happen to match. A place where the average orbital speed of stars and the rotational speed of the spiral pattern coincide. This is called the co-rotation radius. The Sun orbits close to this boundary, and this proximity may be one of the less obvious reasons that complex life was able to develop on Earth. In most regions of the galaxy, stars move at a different speed from the spiral arms. This means they regularly pass through the arms, entering the denser, more active regions where star formation is higher, supernovae are more frequent, and gravitational disturbances are more common. Each transit through a spiral arm represents a period of elevated cosmic hazard for any planetary systems caught within it. A star orbiting near the co-rotation radius, however, moves at roughly the same speed as the arms themselves. It does not regularly cross them. It remains for extended periods in the calmer interarm regions, exposed to lower levels of radiation, fewer gravitational disturbances, and a more stable cosmic environment. This does not make Earth immune to cosmic events, but it may mean that the frequency and severity of disruptions to our solar system has been somewhat reduced. A subtle orbital resonance, maintained across billions of years, quietly contributing to the conditions that allowed life to emerge, persist, and eventually look up at the sky and begin to wonder. The Sun's orbit around the galactic center is not a perfectly flat, perfectly circular path. Like most stars in the disk, it follows a trajectory that is slightly elliptical, bringing it somewhat closer to the galactic center at some points in its orbit and somewhat farther at others. But there is another dimension to this motion that is less commonly appreciated. The Sun also moves perpendicular to the galactic plane. As it travels through the disk, the Sun oscillates gently upward and downward, rising above the plane, reaching a maximum height, then being pulled back by the collective gravity of the disk's mass, passing through the plane, descending below it, reaching a minimum, and being pulled back again. This vertical oscillation repeats on a timescale of roughly 70 million years, meaning the Sun bobs up and down through the galactic plane approximately 3 times for every full orbit it completes around the galactic center. The amplitude of this oscillation is modest. The Sun never strays more than a few hundred light-years above or below the plane before gravity draws it back. But the motion is real, continuous, and measurable. Some researchers have speculated that this vertical bobbing might have consequences for life on Earth, that periods when the solar system passes through the denser regions of the disk or through concentrations of molecular clouds might correlate with increased rates of comet impacts or elevated cosmic ray exposure. The evidence for such connections remains uncertain and debated. What is not debated is the motion itself. The Sun is not gliding smoothly through the galaxy on a fixed course. It is swaying, gently, rhythmically, over tens of millions of years, like something adrift on the slow swell of a vast and patient sea. We have encountered dark matter several times already in our journey through the Milky Way, the invisible substance that holds the galaxy together, that explains the unexpected flatness of its rotation curve, that outweighs all visible matter by a substantial factor, and that forms the enormous halo within which the disk and everything it contains is embedded. Dark matter is, by any measure, the dominant form of matter in the galaxy, and we have essentially no idea what it is. This is not a casual admission of ignorance. It is one of the most consequential open questions in all of modern physics. Decades of theoretical work and experimental effort at particle accelerators, in deep underground laboratories, with space-based observatories, with increasingly sensitive detectors of every kind, have failed to identify the particle or particles responsible for dark matter's gravitational effects. Various candidates have been proposed over the years. Weakly interacting massive particles, WIMPs, were for a long time the leading theoretical candidate, and enormous experimental programs were built to detect them. So far, none has succeeded. Other possibilities include axions, sterile neutrinos, primordial black holes formed in the early universe, and a range of more exotic theoretical constructs. What we know is limited to what dark matter does. It gravitates. It does not emit, absorb, or reflect electromagnetic radiation of any kind. It appears to interact with ordinary matter only through gravity. It is distributed in a smooth, roughly spherical halo around galaxies like the Milky Way, and its presence is inferred entirely from its gravitational influence on the things we can see. It is the most abundant form of matter in the galaxy, and it remains, in every meaningful sense, completely unknown. When we picture the Milky Way, we picture the disk, the luminous, star-rich, spiral-armed structure that spans roughly 100,000 light-years and contains the vast majority of the galaxy's visible matter, its stars, its gas clouds, its stellar nurseries, its ancient clusters. It is an enormous structure by any human measure, and yet it represents only a small fraction of the Milky Way's total mass. The true bulk of the galaxy lies beyond the disk, in the dark matter halo, that vast, invisible, roughly spherical region that envelops the entire visible structure and extends far beyond it. Estimates of the halo's true extent vary, but it may reach several 100,000 light-years from the galactic center, 2, 3, or even more times the diameter of the luminous disk itself. And throughout that enormous volume, dark matter is distributed in quantities that dwarf the mass of everything we can see. The total mass of all the stars in the Milky Way is enormous by human standards, perhaps 50 to 60 billion times the mass of the Sun. The gas and dust of the interstellar medium add a further quantity. But the dark matter halo is estimated to contribute many times more than both of these combined. Some estimates place the dark matter component at 10 or more times the mass of all visible matter in the galaxy. This means that when we look at the Milky Way, at its beautiful spiral arms, its glowing central bulge, its stellar streams and clusters, we are seeing a small illuminated surface atop an invisible mountain. The disk is the part of the galaxy that glows. The halo is the part that matters, in the most literal gravitational sense of that word. Today, the center of the Milky Way is relatively quiet. Sagittarius A star, the supermassive black hole at the galactic core, consumes matter at a modest rate, producing occasional brief flares of X-ray and infrared radiation, but nothing remotely approaching the sustained, brilliant violence of the most active galactic nuclei observed elsewhere in the universe. By the standards of its kind, our galaxy's central black hole is dormant. But there is growing evidence that this was not always the case. The Fermi bubbles, those enormous lobes of gamma-ray emission extending tens of thousands of light-years above and below the galactic center, are difficult to explain without invoking a period of dramatically elevated activity from Sagittarius A star in the relatively recent cosmic past. The energy required to inflate such structures is enormous, far beyond what the current trickle of infalling matter could produce. Additional evidence comes from observations of gas clouds in the galactic halo that appear to have been illuminated and ionized by a powerful burst of radiation from the galactic center, a burst that would have been visible tens of thousands of light-years away and would have lit up the surrounding intergalactic medium with the intensity of a quasar. A quasar is what results when a supermassive black hole consumes large quantities of matter rapidly. When gas falls inward in great quantities, heats to extreme temperatures in an accretion disk, and radiates energy across the electromagnetic spectrum with a brightness that can outshine entire galaxies. Some of the most luminous objects in the known universe are quasars in distant galaxies. The Milky Way, it appears, may once have been one of them. The silence at its center today is the silence that follows a great fire, deep and full of echoes. There is a tendency, when thinking about the cosmos, to imagine galaxies as fixed and eternal, grand structures that formed long ago and have remained essentially unchanged ever since, too vast and too ancient to be meaningfully affected by the passage of time. The Milky Way, in this view, is simply the backdrop against which smaller, faster events take place. But this view is mistaken. Galaxies are not static. They evolve continuously, significantly, and in ways that accumulate into profound transformation across the timescales of cosmological history. The Milky Way of today is measurably different from the Milky Way of a billion years ago. Its star formation rate has declined. Its gas reserves have been partially depleted. Stars formed in earlier epochs have aged, evolved, and died, enriching the interstellar medium with heavy elements and changing its chemical character. The satellite galaxies that orbit it have been slowly consumed, their stars redistributed through the disk and halo. The warp of the outer disk has shifted. The bar at the center has strengthened and settled. Even the dark matter halo has continued to grow, drawing in material from the surrounding cosmic web. And a billion years from now, the differences will be even greater. The Magellanic Clouds, currently on what may be their first approach, will have passed closer and left their gravitational mark on the disk. The pace of star formation will have declined further still. The oldest stars will have faded. New ones, born from gas not yet gathered, will have taken their place. The Milky Way we inhabit is not the Milky Way that was, and it is not the one that will be. It is a snapshot, one frame in a long, slow transformation that began before the Earth existed and will continue long after it is gone. When two massive objects spiral toward each other and merge, two black holes, two neutron stars, or a black hole and a neutron star colliding in the violent final moments of a long orbital decay, they do not simply produce light and heat and matter. They disturb the very fabric of space-time itself, sending outward in all directions a ripple that travels at the speed of light and passes through everything it encounters. These are gravitational waves. Predicted by Einstein's general theory of relativity over a century ago, and first directly detected in 2015 by the LIGO Observatory, they represent an entirely new way of observing the universe. One that does not rely on electromagnetic radiation of any kind, but on the distortion of space and time itself. The waves detected so far have been produced by mergers in distant galaxies, often billions of light-years away. By the time they reach Earth, they are fantastically faint, stretching and compressing the distance between objects by an amount smaller than a fraction of the diameter of a proton. And yet they are measurable, with instruments of sufficient precision. More diffuse than the individual merger events detected so far is the gravitational wave background, a continuous low-frequency hum produced by the accumulated mergers of supermassive black holes throughout the universe across cosmic time. Pulsar timing arrays, networks of precisely monitored pulsars distributed across the galaxy, have recently found evidence for this background signal, using the Milky Way's own clockwork pulsars as a vast gravitational wave detector. Even now, as you rest, space-time is moving. The galaxy is vibrating, at frequencies too low and amplitudes too small for any human sense to register, carrying news across billions of light-years of events so violent they reshape the geometry of space itself. The majority of stars in the Milky Way's disk follow orbits that are, if not perfectly circular, at least broadly well-behaved, relatively flat, relatively round, remaining close to the galactic plane and completing their journeys around the center in an orderly and predictable manner. These stars participate in the general rotation of the disk, moving in the same direction at broadly similar speeds relative to the center, in a choreography that has persisted for billions of years. But there are stars in the galaxy that follow entirely different kinds of paths. Stars whose orbits are dramatically elongated, stretched into long ellipses that carry them deep into the inner galaxy at one extreme and far out into the halo at the other. Stars whose orbital planes are tilted at steep angles to the galactic disk, carrying them high above and far below the plane on each passage. Stars that move in the retrograde direction, counter to the galaxy's main rotation, on trajectories that have nothing in common with their neighbors. These anomalous orbits are signatures. They mark stars that did not form in the disk, or that were removed from orderly disk orbits by some dramatic event in the past. Many are thought to be the remnants of dwarf galaxies that were absorbed by the Milky Way, their stars inheriting the orbital characteristics of their parent system even as that system was destroyed. Others may be survivors of ancient gravitational upheavals, their orbits permanently altered by close encounters with massive objects early in the galaxy's history. By carefully mapping and analyzing these outlier orbits, astronomers reconstruct the galaxy's invisible history, finding in the motion of individual stars the echoes of collisions, disruptions, and mergers that left no other visible trace. There is a form of matter so elusive that it was once seriously doubted to exist at all, not because there was any shortage of it, but because it interacts so weakly with ordinary matter that detecting it borders on the miraculous. These are neutrinos, tiny, nearly massless particles produced in enormous quantities by nuclear reactions and streaming through the universe in numbers that are almost beyond comprehension. The Sun alone produces approximately 10 trillion neutrinos every second, a number so large it resists meaningful visualization. These particles travel outward in all directions at very nearly the speed of light, and within about 8 minutes of their production, they reach the Earth. Every second, roughly 65 billion solar neutrinos pass through every square centimeter of your body, passing through your skin, your organs, your bones, and continuing out the other side without any interaction whatsoever. They do not slow down. They do not deflect. They barely notice that the Earth or you are there. Beyond the Sun, the galaxy produces neutrinos from supernovae, from the nuclear burning of billions of other stars, and from cosmic ray interactions in the interstellar medium. Neutrinos carry information from environments no light can escape, from the collapsed cores of dying stars, from the interior of supernovae during the first fractions of a second of the explosion, before the shock wave has even reached the surface. Detecting them requires extraordinary measures, vast tanks of ultra-pure water or ice buried deep underground or beneath Antarctic ice sheets, where the rare collision of a neutrino with an atomic nucleus produces a brief, faint flash of light. Each captured neutrino is a message from somewhere in the galaxy's hidden interior, delivered silently through everything that stands between its source and our detectors. The galaxy speaks to us in particles we can barely hear, and it speaks to us constantly. We have established that the interstellar medium is not empty, that it is a complex mixture of gas, dust, plasma, and magnetic fields, threaded through the disk and halo in a state of continuous activity. But there is a further quality of this medium that deserves its own attention, because it shapes galactic processes at every scale and in ways that are still not fully understood. The interstellar medium is turbulent. Not turbulent in the way that a stream over rocks is turbulent, or even in the way that a storm system in an atmosphere is turbulent, though these are useful analogies. The turbulence of the interstellar medium operates over distances of light years and timescales of millions of years. It is slow by everyday standards and vast. But it is turbulence in the genuine physical sense, a cascade of energy from large scales to small, a disordered and multi-scale flow of material driven by inputs of energy at many points throughout the medium. The energy that drives this turbulence comes from multiple sources. Supernovae inject enormous quantities of energy into the surrounding medium, launching shock waves that expand outward, sweeping up material and generating turbulent motions as they slow and fragment. The winds of massive stars drive similar, if less powerful, disturbances. Gravitational instabilities in the disk stir gas on large scales. Even the rotation of the galaxy itself, with its differential speeds at different radii, contributes to the overall disorder. This turbulence has consequences that ripple through the entire structure of the galaxy. It affects how quickly gas clouds cool and condense, and therefore how quickly and how readily they form stars. It influences the propagation of cosmic rays, which scatter off the irregularities in the magnetic field that turbulence creates and maintains. It redistributes energy and momentum throughout the disk, connecting the large-scale dynamics of the galaxy to processes occurring on the scale of individual star-forming clumps. The interstellar medium is not a still pond. It is an ocean in permanent slow-motion storm, and the galaxy's life unfolds within it, shaped at every turn by its restless motion. Among the most striking revelations of recent planetary astronomy is the realization that not all planets orbit stars. Some planets, perhaps a great many of them, travel through the galaxy entirely alone, unbound to any stellar system, drifting through the darkness of interstellar space on paths determined only by the large-scale gravity of the galaxy itself. These are called rogue planets, or free-floating planets, and the Milky Way may contain billions of them. They form in two primary ways. Some are born normally, within the protoplanetary disks of young stars, and are subsequently ejected from their systems by gravitational interactions. In the chaotic early history of a planetary system, when multiple planets are still settling into stable orbits, close encounters and gravitational scattering can fling a planet outward with enough velocity to escape the star's gravitational pull entirely. The planet then continues outward into the interstellar medium, free. Others may never have been bound to a star at all, forming directly from small collapsing gas clumps in molecular clouds, in a process analogous to star formation but at much lower masses. Once free, these worlds are extraordinarily difficult to detect. They emit no starlight to reflect and no fusion energy of their own, only the faint warmth of residual heat from their formation, slowly radiating away into space. Gravitational micro-lensing surveys have provided statistical evidence for their existence and hint at populations far larger than previously expected. In the outer halo, where stars are sparse and the darkness is most complete, some of these orphaned worlds may drift on paths that carry them far from any sun, on journeys that will last longer than the current age of the universe. Cold, dark, and silent. Each one a world that formed and was never claimed. Interstellar dust, those microscopic grains of carbon, silicates, and ice that drift through the galaxy in vast clouds and diffuse distributions, does not move through space as passively as it might appear. It is subject not only to gravity and radiation pressure, but also to the influence of the galaxy's magnetic field. And this influence shapes the dust in ways that leave measurable signatures across the sky. Dust grains in the interstellar medium are not perfectly spherical. Many are elongated, irregular in shape, with a longer axis and a shorter axis. When such a grain rotates in the presence of a magnetic field, it tends to align its longer axis perpendicular to the field lines, a process driven by complex interactions between the grain's spinning motion and the magnetic torques acting upon it. Over time, large populations of dust grains in a given region of space become preferentially aligned in the same orientation, all pointing the same way relative to the local magnetic field. This alignment has an observable consequence. When starlight passes through a cloud of aligned dust grains, it becomes slightly polarized, its electromagnetic oscillations preferentially oriented in a particular direction rather than randomly distributed. By measuring the polarization of starlight across different regions of the sky, astronomers can map the orientation of the magnetic field along the line of sight, tracing the galaxy's magnetic structure across vast distances. In some regions, dust grains spin fast enough, driven to high rotation rates by the pressure of starlight, to emit their own faint microwave radiation. This spinning dust emission is one of several foreground signals that cosmologists must carefully account for when studying the cosmic microwave background, the ancient light from the early universe that pervades all of space. Even the smallest particles in the galaxy, it turns out, carry information about the largest scale structures within it, their silent magnetic dance encoding the shape of fields that span thousands of light years. For decades, the prevailing explanation for the origin of the heavy elements was reasonably well understood, at least in outline. Lighter elements were produced in the Big Bang. Heavier ones, up to iron, were forged in the cores of stars through successive rounds of nuclear fusion. Elements heavier than iron, which cannot be produced by fusion in the standard stellar interior, were thought to be created primarily during supernovae, in the intense and brief conditions of the explosion itself. But as observations improved and computational models became more sophisticated, a problem emerged. The amounts of the heaviest elements, gold, platinum, uranium, and others, did not match what stellar explosions alone could produce. Something else was needed. Some other site of nucleosynthesis, capable of producing the extreme neutron densities required to build the very heaviest nuclei. That something else, it now appears, is the collision of neutron stars. When two neutron stars, the extraordinarily dense collapsed remnants of massive stellar deaths, spiral together and merge, the result is one of the most energetic events in the observable universe. A kilonova. In the extreme environment of the merger, neutrons are captured by atomic nuclei at a rate so rapid that it builds heavy elements faster than they can decay. A process called the rapid neutron capture process, or R process. Gold, platinum, and a range of other heavy elements are synthesized in enormous quantities during the first fractions of a second of the collision, and then scattered into the surrounding space as the merger drives an outflow of enriched material. The gold in a wedding ring, the platinum in a laboratory instrument, the uranium in a reactor. All of it was forged in the collision of dead stars scattered across the galaxy by the violence of their meeting, and eventually gathered into the cloud that formed the solar system. Some stars in the Milky Way show the chemical fingerprints of these events, elevated abundances of R-process elements that can only be explained by the nearby detonation of a kilonova somewhere in their ancestral gas cloud. They carry in their spectra the memory of a cataclysm that produced some of the rarest and most familiar substances on Earth. We have already discussed the central bar of the Milky Way, that elongated, slowly rotating bridge of densely packed stars that crosses the galactic center and shapes the dynamics of the inner disk. It is a significant and well-established feature of the galaxy's structure, identified through infrared surveys that can penetrate the dust clouds obscuring the core. But within that bar, there may be another one. Astronomers studying the kinematics of gas and stars in the innermost regions of the galaxy, within a few thousand light-years of the center, have found hints of a secondary structure. A smaller inner bar nested within the larger one, oriented at a different angle and rotating independently on its own timescale. The evidence for this inner bar is less direct than for the outer one. The extreme dust obscuration of the galactic center makes detailed observation enormously difficult, but its gravitational influence appears in the motions of nearby gas clouds and stellar populations. If it exists, this inner bar would have significant consequences for the dynamics of the galactic core. Bars are efficient at transporting gas inward along gravitational pathways, a process called inflow, and a nested pair of bars rotating at different rates and interacting through their combined gravitational fields could create particularly effective channels for funneling material toward the supermassive black hole at the center. This, in turn, could influence the rate at which Sagittarius A star is fed, and potentially the frequency and intensity of its periodic outbursts. The center of the Milky Way, already known to be a place of extraordinary complexity, a supermassive black hole, a peanut-shaped bulge, a rotating bar, dense stellar clusters, may contain layers of structure within layers, each rotating on its own rhythm, each shaping the flow of matter toward the galaxy's silent and powerful heart. The universe is not uniformly distributed. On the largest scales, matter, both ordinary and dark, is arranged in an intricate web of filaments, sheets, and nodes, separated by vast, nearly empty voids. This cosmic web is the large-scale skeleton of the universe, and the galaxies we observe are not scattered randomly within it, but concentrated along its filaments and at the intersections where filaments meet. The Milky Way sits within this web, and it is not a passive inhabitant. It actively accretes material from the filaments around it, drawing in gas that flows along the cosmic web's threads and falls gradually inward under the influence of the galaxy's gravity. This infalling gas arrives in several forms. Some comes in as cold streams, long, thin filaments of relatively dense, cool gas that penetrate deep into the galaxy's halo before heating and mixing with the hotter gas already present there. These cold streams are thought to be a significant contributor to the supply of star-forming material in the disk. Other gas arrives already heated, shock-heated as it falls into the galaxy's gravitational potential well, radiating in ultraviolet and X-ray light as it slows and settles. The rate of this accretion varies over time. In the galaxy's early history, when the cosmic web was denser and the surrounding intergalactic medium richer in cold gas, inflow rates were substantially higher, helping to fuel the elevated star formation rates of the galaxy's youth. Today, the flow continues, but more modestly, sustaining a galaxy that has moved past its most productive phase, but has not yet exhausted its supply of raw material. The Milky Way is not self-contained. It breathes in from the universe around it, drawing substance from the largest structures in existence, converting cosmic web filaments into stars and planets, and perhaps the conditions for life. When a single massive star dies in a supernova, it releases energy equivalent to the sun's entire lifetime output in a matter of seconds. That energy expands outward as a shockwave, carving a cavity in the surrounding interstellar medium, a hot bubble of rarefied gas surrounded by a shell of swept-up material. These individual supernova remnants are striking and well-studied objects, expanding slowly over thousands of years until they merge with the general turbulence of the interstellar medium. But supernovae rarely happen in isolation. Massive stars tend to form in clusters, and because they are massive, they live short lives and die in rapid succession, one after another, over periods of millions of years, in the same general region of space. When this happens, the individual supernova remnants overlap and merge before they have time to dissipate, combining their energies into a single enormous structure called a superbubble. A superbubble can span hundreds of light-years, a vast hot cavity of plasma, its interior emptied of most gas and dust, its walls a compressed shell of interstellar material lit up by the energetic radiation of the massive stars within. These structures can grow large enough to reach the boundary of the disk itself, and when they do, they can break through. Above and below the galactic plane, the density of gas drops sharply. A superbubble that punches through the disk encounters this lower pressure environment and expands rapidly upward and downward, venting its contents into the halo in structures called galactic chimneys, towering columns of hot gas, magnetic fields, and cosmic rays rising tens of thousands of light-years above the disk. Through these chimneys, the galaxy breathes outward, expelling the products of stellar death into the halo, where they cool, condense, and eventually return downward in the slow rain of the galactic fountain, completing a cycle of circulation that keeps the disk in chemical and energetic balance. The Milky Way that our eyes perceive, the gentle band of starlight crossing a clear, dark sky, is only one version of the galaxy. Viewed through the lens of X-ray astronomy, the same galaxy reveals an entirely different face. One that is hotter, more violent, and populated by objects of extraordinary density and energy. X-rays are produced by matter at extreme temperatures, millions of degrees, far beyond anything encountered in ordinary stellar physics. In the Milky Way, several classes of objects reach these temperatures routinely. Neutron stars and black holes in binary systems are among the most powerful X-ray sources in the galaxy. When a compact object, a stellar remnant so dense that a teaspoon of its material would weigh millions of tons, orbits a normal companion star, its gravity draws material from the companion. This material does not fall directly inward. It forms an accretion disk, a swirling structure of infalling gas that heats to millions of degrees through friction and compression as it spirals toward the compact object. At these temperatures, the disk radiates intensely in X-rays, producing a persistent and often variable glow detectable across the entire galaxy. The remnants of supernovae, the expanding shells of hot gas left behind by stellar explosions, also glow in X-rays, sometimes for thousands of years after the initial detonation. The hot gas permeating the galactic halo, heated and maintained by supernova outflows and galactic chimneys, emits a diffuse X-ray background that traces the galaxy's large-scale thermal structure. Space-based X-ray observatories, including Chandra, XMM Newton, and more recent instruments, have spent decades mapping this high-energy face of the Milky Way. What they reveal is a galaxy that simmers beneath its calm optical surface, shot through with pockets of extreme heat and populated by objects whose physics operates at the very limits of what matter can do. When a massive star exhausts its nuclear fuel and collapses, the core, if it falls within the right mass range, does not become a black hole. Instead, it becomes a neutron star, an object roughly the mass of the Sun compressed into a sphere perhaps 20 kilometers across. At these densities, the very structure of matter changes. Electrons are forced into atomic nuclei, merging with protons to form neutrons. The result is a body so dense that a single teaspoon of its material would weigh hundreds of millions of tons. Many neutron stars rotate. They were rotating as stars before their collapse, and conservation of angular momentum, the same principle that spins a figure skater faster when they pull in their arms, dramatically accelerates that rotation as the collapsing core shrinks from a sphere the size of the Sun to one the size of a city. Some newly formed neutron stars spin hundreds of times per second. As they rotate, neutron stars emit beams of electromagnetic radiation, radio waves, X-rays, gamma rays, from their magnetic poles. If these poles are not perfectly aligned with the rotation axis, the beams sweep through space like the beam of a lighthouse. When the Earth happens to lie in the path of one of these beams, we detect a pulse of radiation each time the neutron star completes a rotation. These are pulsars, and their pulses arrive with a regularity that rivals the most precise atomic clocks ever built. This extraordinary precision makes pulsars scientifically invaluable. By monitoring the pulse arrival times of many pulsars distributed across the galaxy, astronomers can measure distances, test the predictions of general relativity with great precision, and, as recent observations suggest, detect the background hum of gravitational waves passing through the galaxy. Across the Milky Way, hundreds of known pulsars tick away in the dark. Remnants of destruction, instruments of remarkable order, blinking steadily through the silence between stars. Visible light, for all its familiarity and richness, is a poor guide to the full structure of the Milky Way. Interstellar dust absorbs and scatters it over distances of a few thousand light-years, blocking our view of the vast majority of the disk. The galactic center, the most structurally important region of the galaxy, is entirely invisible to optical telescopes, hidden behind layers of obscuring material so thick that not a single photon of visible light from the core reaches us directly. Radio waves experience no such limitation. With wavelengths millions of times longer than those of visible light, they pass through interstellar dust without significant absorption, traveling freely across the full extent of the galaxy and arriving at our radio telescopes, carrying information from regions that visible light can never reach. The most important radio signal for mapping the Milky Way is emitted by neutral hydrogen, the most abundant element in the universe. When the electron in a hydrogen atom flips its spin relative to the atom's proton, it releases a photon of radio light at a precise and specific wavelength, 21 centimeters.